Good morning, everyone. Maybe good day. See, the number of people attendees are still increasing. Or maybe give a few minutes here so everybody joining us. Shall I start like in 1 to 2 minutes here? All good. So good day, everyone. My name is Hamid Behmanesh. I'm joining you from Calgary, Alberta. It's a very beautiful morning here. I can imagine it is 10 degrees centigrade in Calgary in late February. We're gonna hit 10 degrees this afternoon. It is really impressive. And by the way, last week it was minus 30. So I get so excited ahead of myself. And so for today course, this is a brand new course as a brand new feature that we implemented in the software. And this course is actually the first time being offered. And it's my pleasure to have another opportunity to be with you and talk about pressure transient analysis. It's actually, so far we have been talking about rate transient analysis. Pressure transient analysis is actually his cousin. So it has been there for much longer than RTA. And we're going to see what exactly we can dig into PTA when it comes to analyzing the data. So let's go ahead. So this is a term of the meeting logistics. 80 plus people register for this course. Hopefully more people will show up. We're going to present this content in 3 hours. And if you have any question, please leave it in the chat box. There are good colleague of mine will be able to help you with those questions. But if there are some other question related to the content, etc., that we can have a in-depth discussion during the break time. So most of you hopefully are Whitson clients and you're very familiar with Whitson Plus, Whitson PVT, Whitson X. These are all the software that we have. And today's focus is mainly on the Whitson Plus. And announcement here. Later in March 16, we will be holding with Canada. I highly encourage you to take a look at the website and take a look at the agenda because one of the talks at least is about water disposal valve and how the operator do the injection fall-off test to come up with some reservoir properties. So that should be exciting. I'm looking forward to taking a look at that and also include some example here, at least in terms of the pressure and rate. So how the injection fall off would look like. So take a look at that. And we're also sending out emails every week under the name Whitson Weekly. And in this newsletter, we included many information regarding the events and webinars and courses. So if you're not part of Whitson Weekly, please contact Jessica and she will be gladly include your email address into the listing as well. So certificate, most of you are familiar with the certificate. The PTA certificate is not yet there. So we decided to include this course first and roll it out and receive some feedback from you guys. So it's very important for myself personally to receive some feedback from you on the content and the level of the content being presented, the number of example, how they feel it, and what other example you wish to look at. And so if you communicate those feedback with me, so it will be really helpful for us to fine tune and make those certificate custom to you. Of the support, many of you has experience with the support. We treat every ticket on there, try to get back to you as soon as possible. So with the software, what we're going to cover today is mostly the PTA stuff. So with the login and access, we're going to make sure that you guys have access to the software. So, and we're going to load some example there. And we're going to show you a good chunk of this talk will be focusing on the content, like the underlying content. And a good chunk of that is also clicking on the software and see what are the capability that we so far we have implemented in the PTA. And mainly on the PTA, and so far we included drawdown and build up. There are a ton of different tests in the world of conventional PTA, but so far we have included drawdown build up with a focus on the build up. And this is injection fall-off going to be a next addition for this because injection fall-off is essentially in terms of the mass identical to drawdown build up, except that we need to treat rates as a negative rate. That's how we get increasing pressure, right? And so before going through the content, I'm going to make sure everybody access to the course content. So if you don't mind, please go to Whitson, the courses.whitson.com. And underneath the course, you should be able to see this PTA in Whitson. If you don't see that, please let us know. And once you see that, please go ahead.
Yeah, Hamid, we don't see it.
We don't say, okay, so
Yeah.
I think I have to go ahead and Felix, could you please make sure that this course is not private? So I have to make it company-wide. Say, thank you for letting me know. If you refresh your page, now you should be able to see the PTA in Whitson. If you don't see it, please let me know. And once you see it, you can click into to go through the field, and you can add a project here on the top and create a project under your name so it is unique to you. So what I'm gonna name this one, I'm gonna call it Hamid PTA Calgary. So this is my project name. Click on save, and when you click on save, you should see your name on the project, underneath the project, Hamid PTA Calgary. And once you are here, please go to mass upload. In the mass upload, click on the example. It's very similar to the certificate, in a certificate that you earn, the well test certificate. So I guess I have to contact Henrik because you're supposed to see some certificate here. Let me contact
I'll
Henrik.
fix it.
Okay, thank you, sir. Yeah.
Thanks.
So you should be able to see some PTA certificate vaults, and we're gonna load these vaults. We don't want to do anything with this vault right now, but we're gonna go to the slide deck. So we're supposed to see this vault certificate, and then we're gonna work on those vaults. There are 13 of them, and each of those vaults are prepared with some intention to see during the course. Okay, so with the introduction on the PTA, it's very important to get to the introduction. If you get the fundamentals down, then the level of everything will rise. So this is what I believe, and I'm going to walk you through some of the well test fundamental. And first, this is named as a conventional well testing, or PTA. What's the difference between well testing, pressure transient analysis, well test interpretation, conventional and unconventional? I'm going to start with this slide, PTA, pressure transient analysis. Never say PTA analysis, RTA analysis, because that's RTA analysis, right? We perform RTA and PTA, but we don't do PTA analysis. So with the pressure transient analysis, what we do, we control the changes in the flow rate, and we measure the pressure, and then we do the analysis on the pressure. And this is identical with what we do with the rate transient analysis. But in the rate transient analysis, we focus on the long-term production rate and pressure data at the sun time. But in the pressure transient analysis work, we only focus on the maybe a week of data or 1, 2, 3 days of the data, depending on the permeability of the reservoir that we are dealing with. And we also have deliverability testing. What's the deliverability testing? It mainly applies to the conventional millidarcy type gas reservoir, where you are trying to understand some mechanism other than the mechanism that happens in the unconventional, like low permeability reservoir, mainly finding the turbulence factor. So this is the turbulence factor goes directly into IPR, absolute open flow, and that's why it is important for us to do some tests like deliverability testing. And lastly, the unconventional testing, we have a dedicated course that focuses on the DFIT analysis as well as pressure interference. So CPG, chow pressure group, and DQI, Devon quantification interference. Underlying physics on the conventional and PTA are very similar. They are not different, but in each of these, we are focusing on different parameters. So that's why we introduced this course as to stand by itself on the conventional pressure transient analysis. All good. So let's move ahead and let's talk about the PTA a little bit. In the PTA, we do analysis of the pressure, and we use all the tools in our toolbox. One of them is the derivative, and I'm going to show you the importance of the derivative for pressure transient analysis, and try to identify the flow regime if you are still in the transient, or if you are in the boundary dominated flow, or if we are dealing with the wellbore storage as well, because any data that we are collecting in the PTA is somehow has the trace of both wellbore and the reservoir. But the ultimate goal of PTA is focused on the reservoir side of the thing. With the reservoir, we are interested in getting the permeability, getting the boundary of the reservoir if there is any fault, or if there was the permeability and boundaries of the reservoir. But those information that we get, it goes through the wellbore, right? So and ultimately, what we are collecting on the surface is a combination of the reservoir and wellbore itself. So we should be able to decouple them. It's dealing with heavily with math. It's dealing with the diffusivity equation, Laplace, superposition, those sort of stuff. So essentially, it's a solution to a problem, and solving the pressure response with diffusivity equation. What goes beyond that is a well-test interpretation. Well-test interpretation is a big umbrella with the PTAs underneath this umbrella. In the well-test interpretation domain, we do the quality of data control. Okay? We look at the data, talk to the data, let the data talk to us as well, and decide if this data worth being analyzed in the PTA world or not. That's again important part. Now, there are definitely much more beyond that. One of them is like the pressure data is coming from the gauge. The gauge could malfunction, the gauge could be hydrated, the gauge could be clogged, the gauge could drift. So all of those could happen. The phase redistribution and phase distribution in the wellbore is also a big part of that. Multi-phase effect. All the PTA work fundamentally deal with the single phase, oil and gas. But in truth of the matter is that they're producing water, oil, gas, all at the same time. So what would be the result of analysis if our data is impacted by those multi-phase flow? So there are very much more beyond that. Fracture geometry, how if the fractures are infinite conductivity or finite conductivity, that's another thing that we can get from the well-test interpretation. And also a stress-dependent permeability. So in short, well-test interpretation is understanding the actual well and reservoir behavior. Once we understand it, we're going to transfer it to PTAs. But this is the primary step. We need to spend 50% of our time dealing with these before filtering our data for the PTA work. In terms of the type of the test, this is a typical data that we receive as the period of drawdown. So we call it this drawdown test. You can do the analysis on this part of the data, but look at the data in terms of the pressure is jumping all over the places. And imagine you're going to take the derivative of this data. In some cases, the derivative also works fine in the drawdown work. But in many cases, you got cloud of the data. There's no directionality towards that. That's why we do PTA on the build-up side of the thing. Why 95% of the cases we simply do pressure transient analysis on the build-up. We can do pressure transient analysis on the drawdown. That's essentially what translated in terms of rate transient analysis. But if you're going to get a good estimate of the our permeability, damage stimulation, boundary, or sometimes initial reservoir pressure, or whether focus on the build-up side of the thing, simply it's much cleaner data. The derivative works much better in this world. Once we collected this data, now what we're going to do with that? So once we collected this data, the first thing that we're going to do, we're going to plot this data versus time, versus actual time. We're going to see if there's any anomaly in the data. That's why we plot the data in the software. If you go to the software, you will see the data will be plotted against the actual time. And you will be able to identify if there's any anomaly. If there's a nearby operation, if they're doing gas injection or they are fracking another well in a nearby, you're going to see those data being impacted, how the pressure is building up in this some part of this this build-up data that we collected. So that's why it is important to look at the data in the first place in the time domain. Next, we're going to distort this data and we're going to plot them on any type of the plot that we can get. In this case, I'm plotting the data delta P or versus log of some sort of log of time. And when I plot the data, you see that the data I get, at least at some part of the data, are presenting itself as a straight line. And a straight line is something that I love to see on my plots because I can, through a straight line, do a straight line analysis and get some information. Hopefully, I can get those. But before that, I can see there's a dip in my data. So what could be the source cause of this dip? And at the end, the tail of the data is also flat. So that's something that I need to investigate. Maybe if I plot my data versus the square root of time, the last part of the data stay flat and the early time stay also flat. So I don't know what exactly could be could I plot. And let's talk about the derivative a little bit. With the derivative also, we can plot on the log-log plot to identify if there's any signature with the data, or I can also plot them on the log-log plot. This is also log-log plot of the data. This is also log-log plot of the data. But this derivative is different from this derivative that we see here. It's simply because the definition of the derivative is different for these two cases. One of them is with respect to time. One of them is Bourdais derivative. And each of those has its own implication. And I'm going to talk about that a little bit as well. So when I plot the data, the semi-log plot versus log-log plot, I see a straight line here, I see a horizontal line in the middle of the data, and then the data dips. And also remember, by log-log plot, if you have 100 days of the data and you plot it on the log-log plot, on the semi-log plot at least, they're going to be 2 log cycle. The first log cycle is going to be between 1 day and 10 days. The second log cycle is going to be between 10 days and 100 days. So what log plot do is expand the early time data where everything is dominated by wellbore and near wellbore, and contract the late time where everything is dominated by the reservoir, bulk of the reservoir effect. And finally, if I plot my versus the square root of time, I see all sort of curvature. So that's not my favorite plot to look at for this sort of the data. So the ultimate goal of PTA is to plot the data in different scales and see if I can get any straight line out of the data, because I can work with a straight line much easier than I can work with a curved line data. So if nature in charge is all the vessels and veins and in the anatomy of the head would be something like that. If reservoir engineering is in charge, or any, I don't know about other engineers, this is what they're going to see. So if they ask to consult in creation of another generation of human, they're going to come up with all the veins to be in a straight line, right? And simply because engineers love a straight line, and if you don't believe me, this is one of the support ticket that we receive. The engineer was complaining why I cannot draw a straight line between 2 lines in the PNR DCA, and I'm sorry to disappoint him that we need at least 3 data points so we can run PNR DCA on this well. So that's why a straight line analysis is very favorable to us, and we're going to focus on that a lot. So let's focus on the fundamentally on some of the tests that we do in the PTA world. Drawdown and build up, they're always coupled. We can do analysis of drawdown by itself, but as you know, it's very noisy data, especially with the bottom hole pressure. So I would rather put it on build up, get a clean profile on the build up, and to do build up analysis. Multi-rate test, this is very common in the conventional gas reservoir, where we are interested in finding some reservoir parameters like turbulence factor. A step rate test is another type of the test that we do for finding the reservoir fracture pressure and injection follow. For each of these tests, I'll provide some examples so you have some idea what we are talking about. And some tests are designed in order to have some idea about the boundary of the reservoir. If we can identify any reservoir limit, the reservoir limit could be the well that's competing for the reserve next door, or it could be a fault, or it could be a no-flow boundary, or it could be an aquifer. And therefore, we do also interference tests. This is very common in the unconventional world as well, with the toe pressure group and DQI. And we also do pulse tests. I show some example of these. And exploration and formation evaluation tests. These are some of the tests we have been contacted by one of our clients regarding they are interested in exploring hydrogen. And the hydrogen, so with the hydrogen exploration, the test that we need to run should be very small, like short time period. That's why these tests are designed for those specific ones. And there are some other tests like static and flowing gradient. This is where we are interested to understand how the liquid level is changing and evolving in the wellbore. And AWS, that's acoustic well sounder. People also do that routinely to find out what's the liquid level. For instance, if the well is equipped with the plunger leaf, they're going to see what's the liquid level in the casing side in the annulus. They're going to do this AWS wells. So the good definitely is talking about designing a test in the PTA world. The cost of a good test is definitely visible. The cost of a poor test is hidden. If you're going to translate it in the pressure transient domain, PTA domain, we need to require shut-in, operational consideration, and defer production. All of this definitely costs some money for us. Yeah, but if we poorly design our test, we got some ambiguous data interpretation and incorrect reservoir decision, that definitely the cost would be much more in the order of magnitude different. So it's definitely makes sense to pay the good money to get a good test with a good reliable data set, so we can do some confidence do the interpretation rather than do a poor test and the data now is not analyzable at all. This is a drawdown test, very familiar in the RTA world. This is a build-up test. We're going to focus on analyzing this part of the data. This is the multi-rate test. So mainly it is good for conventional millidarcy type permeability. What we're going to do, we're going to produce it for a while. So we got some stabilization in the pressure. We're going to collect this PWF at the end of each period. And we're going to plot in such a way that we get turbulence factor. Next test is the pulse test. So we produce and shut it, produce and shut it. These are the pulse that are propagated into the reservoir. And there's a monitoring valve that's collecting these pulses. Depending on the strength of this pulse and how the pulse are propagating in the reservoir, we're going to identify some of the reservoir characteristics. What is the objective of well testing? So I'm going to pose some question to you, and before revealing these answers, I want you to just give it a couple of seconds, give it some thought, and see what would be your strategy for in these cases. So the problem statement here is if you have two wells and both of them are producing at a constant rate of 500 STB per day, and we confirm through some monitoring, seismic, I don't know, whatever you call it, that they have both identical original fluid in place. These wells definitely are very identical because they are producing the same rate and they exit the same volume. But which well would you select if you are given the chance to? And what are the reasons? Right. So before revealing the answer, maybe give it some thought. If you come with some strategy, what other information would you like to know about these wells before you select them? And the very easy way to address this question is simply go to the productivity index equation. This is some of the reservoir property, KH, and mu B, and some of the, I see some people address that in the chat. Thank you for those contribution, and some average reservoir pressure, which is definitely depends on the size of the reservoir, and also some scheme, right? So what I provided to you is the rate is the same, average reservoir pressure is the same because they have the same volumetric and same cumulative production, but there are also RE is the same because volumetric is the same, but there's a KH and the skin factor that's all different here, right? So as the well test application, we're going to properly design an injection drawdown as a drawdown build-up test and determine permeability and skin factor. Why those matters? Because that impact long-term recovery potential, as well as it's also impact the economic value of the asset. If my permeability is 100 millidarcy, the other permeability of the well is 10 millidarcy, it definitely impact the well spacing decision-making process in the future. So if I do that, reservoir permeability, I definitely go always, my choice is going to be reservoir permeability. The well that access higher reservoir permeability, I'm going to pick that. Why? That's the mother nature, that I cannot do anything about the reservoir permeability. Stir, I'm going to deal with that, but what I can do, I can deal with the skin factor. I can do acidizing, I can do a small fracture and improve the productivity of the well that way. So this is my solution. It's going to be drawdown and they're going to be build up. I'm going to do the analysis on the build up. Next question. This is a question related to injection follow-up, and aquifer is being considered for CO2 sequestration or water disposal. Same idea here. Formation is thick, laterally extensive, and volumetrically lower. The target formation injection rate is 5,000 barrels per day, right? But here are the excuse me. Here are the concerning question. Actually, if the formation can sustain the rate, if I start to inject at this rate, what would be the surface pressure? Right? And if we continue with this injection rate, would we exceed the fracture pressure? And there are some of the relevant questions that are also very related to this, and gonna give it some thought, and this is the well test application part of that. Again, we're gonna this time, we're gonna design a separate test to come up with the fracture pressure. We're gonna design an injection fall-off test to come up with the reservoir permeability and the steam factor. Those are determined. We're gonna put it in the model and address all of these questions. So this is actually one of the, we're gonna go through this example as well. This is injection and fall off. This is the injection rate for a disposal well in Calgary. That we were somehow involved in analyzing this. And we're gonna take a look at this injection and fall off behavior during the example, when we review the examples. This is another example, and this is looking to identify if there's any fault or sealing fault nearby. And if there is, what is the estimated distance to the boundary? And again, by designing a properly test, we can address if we see any heterogeneity in the reservoir during the duration of the test. Those will be we can address what would be the relevant distance to the location of the well. So this is the result from the interpretation that we did. I also provided this example for as a part of the wells that we will investigate, and we're going to take a look at these data as well. We clearly see two different trends in both on the semi-log Horner plot and also on the superposition on the log-log type curve plot. And we're going to talk about this as well. And lastly, I believe this is the last example, as most of you, I believe, coming from the unconventional world. In the unconventional world, the main question that we are trying to answer, one of the main questions is if the fracture is finite conductivity or are they infinite conductivity. And I included one very nice data set from a dry gas reservoir that we're going to perform RTA and PTA. It has a very extensive shut-in period that gives us that opportunity to compare the result from RTA and PTA and be able to address if it really is a finite conductivity or if it is infinite conductivity by simply looking at the pressure derivative data. And lastly, we conducted a test. This is the initial reservoir pressure. They run the gauge downhole and come up with the estimate of the initial reservoir pressure. They flow it for 20 days and then put it on the buildup. The buildup was so extended that basically the average reservoir pressure is attained because it's plateaued. And what they realized in the first part is that this average reservoir pressure is different from the initial reservoir pressure. So after 20 days of production, come up with the estimate of initial fluid in place. It means that the fluid in place is very small, actually, right? And if the fluid in place is very small, it means does it worth exploration, drilling the well in the same area or not? But it could be very well related to how we collect the downhole gauges and how we convert them to the midpoint of perforation. So we're going to address that as well. So in summary, these are all the information that in some of the tests that we can attain some of this information, not all the tests. Reservoir pressure. So how we can get an estimate of the initial reservoir pressure or average reservoir pressure. Permeability or flow capacity, that's KH in the first example. If there's any boundary or heterogeneity, really depends if we flow the valve for a good period of time. And we're going to deal with that in the flow regime identification to see any fault in the region or not, or any actual physical boundary. Formation, damage, and stimulation, that's the skin part of the thing. Flow regime identification, that essential and critical ingredient in any the well test interpretation. And sometimes we're going to take a fluid sample. In the hydrogen case that I mentioned to you, they're going to conduct a drill stem test and collect some hydrogen sample to see if it is pure hydrogen or some contamination involved. The stimulation design, you have a vertical wall and the skin is 5 plus 5 indicating there's a damage. Now you're going to do some stimulation. You want to see how much acid you need to inject so you can improve the permeability nearby. And also we develop productivity and performance over time. Sometimes regulatory, you need to come. There's some regulatory mandate that you need to run some tests for the integrity of the wellbore for some other tests. Therefore, you need to run those tests. And if you run it properly, you can also gain other information from the test, right? So let's start with the drawdown. If you're gonna start with the drawdown, these are all the ingredient that goes into the bottom hole pressure profile when we put the well on production. The first one is PVT, if you are dealing with the oil well, water well, gas well, or multi-phase, right? The second part of this is definitely the wellbore geometry. It's the vertical, horizontal, multi-frac horizontal well, if the well is damaged or stimulated, or there's a wellbore storage. In terms of the reservoir could be homogeneous, could be isotropic, could be heterogeneous, there could be some fault. It could be multi-layer, which really make it complicated. If it is a multi-layer with distinct permeability across all the layers, then designing a proper build-up test will be really difficult and challenging here. Or if we're going to be composite reservoir or dual porosity. In terms of the boundary of the reservoir, it could be infinite acting. It could be an aquifer injecting into an aquifer, which is infinite acting. Like in the time of the test, it can present itself at infinite acting. There could be a fault nearby. Could be a composite reservoir, or it could be access. The reservoir is connected to an aquifer, which is at constant pressure. Could be no flow, simply because there's another well draining from the same reservoir, and therefore it's a no flow boundary. established in between the two wells, and it could be our channel reservoir. So for the sake of this presentation, we're going to store everything simple. That's the simplest combination of the parameter that we can have, because this simplest combination of parameter also satisfy all of these assumptions, which is required for development of that diffusivity equation that we're going to take a look at that. So as I said, when we collected the data, we present them differently. And in this set of the data that I'm presented to you, I'm going to take a look at the how the pressure is building up, relationship between pressure and force root of time, and some derivative analysis, and also maybe plot the data differently. And simply by looking at a combination of these plots, I will be able to have a better decision on what's really going on physically into the reservoir. Because when I'm plotting the data on the log-log plot, I'm expanding the early time. In the actual time, 1 hour of the data worth the same amount of information at 1 hour of the data at the late time. But in the log-log plot, one log cycle of the data early time is worth the same log cycle of the data late time. But the data here is contracted. That's 90 days of the data in 100 days production. But the first log cycle is 10 days of the data. So that's what we're going to do. Just a little bit talk about the flow regime, because all of them are somehow connected. They are not distinct concept. They are connected. So this is a vertical wall in a radial model, and this is looking at the side. This is how the flow regime is happening. Basically, these streamlines are parallel to each other. This is one single fracture. We can also upscale this one to a multi-fracture horizontal wall. Well, the streamlines are parallel to each other but perpendicular to the face of the fracture. So from the side view, this is the fracture. From the top view, this is the top of the reservoir. This is the flow lines that are perpendicular to the fracture face. And also we have a bilinear flow. In the bilinear flow, there's some flow happening in the face of the fracture, simply because the permeability in the fracture itself is a medium, is low, and therefore for the pressure to propagate from the wellbore itself to the end of the fracture takes some time. Therefore, we are seeing some linear flow inside the plane of the fracture and another perpendicular flow towards the face of the fracture. So these are the flow regime, but in terms of what actually happens is talking about the transient, transitional, and boundary dominated flow. It's like throwing a rock in the middle of a pond. If this is my pond, these are all the ripples are formed, right, radially. By the time this ripple hasn't touched any boundary, the data that I'm collecting at the wellbore won't be able to see the size of the reservoir. It is only when we started to target some of these boundary of the reservoir that we can see, well, it's not anymore transient, but it's in the transitional. By the time we investigated all the dimensions of the reservoir, we called it a boundary dominated flow. So these are simple definition: infinite acting when the ripples are still growing and hasn't touched any of the boundary, and the boundary dominated in where all the boundary are touched. Now I have very confidence in the size of the reservoir. It could be depend really on the flow on the wellbore geometry and the way that we complete it. It could be in the multi-fracture horizontal wall. This is how the transient, transitional, boundary dominated flow will grow, and also depends on the operational activity in the wellbore. If there's a fault, definitely the transitional flow will take much longer time to get into the boundary dominated flow. Or if we drill another well, right, all of these will be impacted. So the flow regime can be constantly evolving. So, but through a properly designed build-up test, we can have a good idea about how the flow regime also evolving as well. Or it could be more complicated, like if you do a refrac in a multi-fracture horizontal well, right? And some of the fracture are bigger than the other ones. So this fracture will be continue to explore some areas that hasn't been depleted yet. So there are still transient flow. But these small fractures are already depleted, and these are experiencing boundary dominated flow. So it's going to be a combination of flow regime, even with one single wall. With the sequence of flow regime, this is a vertical wall, and this is a radial distance, as RW is the radius of the wellbore, RE is the external radius of the reservoir. When we start to produce from the wellbore, The first medium that will contribute to flow is the wellbore itself, because there's a fluid sitting in the wellbore and fluid is compressible. So that's the first medium. And then the pressure starts to propagate, like very similar to the wave and ripples that propagate in the pond. And this is what we're going to see. At some point, we're going to investigate the size of the reservoir, and then we're going to start depleting the reservoir itself, right? That's the flow regime. And if we plot our data, this one, in this case, I'm talking about the drawdown, but in this case, I'm talking about, I'm plotting my data, the build-up data. So you see there are some clear, distinct flow regime here. The early time definitely impacted by the wellbore and wellbore storage. This is the right term to call. And the middle part is simply transitioning from wellbore to reservoir. The middle part is mainly dominated by the reservoir, and the final part is impacted by the boundary of the reservoir. Okay, let's go to some of the equation that we're going to use through the end of this presentation. But the idea is to make this talk mainly concept focus, not equation heavy. With all of these assumptions for this geometry that I'm presenting to you, this is the equation that we're going to deal with. And this equation is very impressive. Those people who solve for this problem with all the Bessel functions of kind 1, 0, and 1. I tried to just get it to ChatGPT to give me a solution, but I tried, and it definitely was not close to what I was expecting. And these two gentlemen, Matthew and Russell, developed this equation in 1967. They're definitely a mathematician, but the complexity of this equation is very scary. But the good side of the thing is we are not dealing with this equation at all. What we're going to deal with this equation is a simplified version of this, which I believe most of you are familiar. Summarized, simplified to early time solution and late time solution. The early time solution is simply this logarithmic behavior, this delta pressure. It's equal to log of time plus some constant. Late time is simply delta P is a function of A times T plus a constant as well. This is the productivity index, right? That I presented in one of the slides in the problem statement number 1. And this is Q times T. We're going to revisit this equation one more time. I'm not sure if we were able to, Mo, maybe you can advise, were we able to grab the equation?
Yeah, you need to just refresh the browser,
awesome.
Hamid,
Thank
and
you,
then
sir.
you should be able to grab the files there.
Perfect.
To do the mass upload.
Thank you, sir. I appreciate the update. So if you go to the project, I see a lot of you guys. Thank you, and have created your own project. So I'm gonna go to my project. If you go to your project as well, Hamid PTA, and then if you click on mass upload under example is the PTA certificate valves, and click on upload, and you will be able to upload all of these. So the first example that I'm going to present, at least to just get familiar with what we're going to see during the remainder of the course, let's take a look at a drawdown test. We don't specifically do drawdown analysis in the PTA module, but what we do is, what I can show you is how to plot these equations to see the behavior of this equation in the early time and late time. So still uploading. So these are the 13 wells that we're going to take a look at on. The one that I'm interested is a reservoir limit test 1. So if you click on reservoir limit test 1, and if you go to PVT, and on the PVT, click on edit reservoir fluid composition. And once you do that, you only need to click on save. PVT
Maybe just give like 30 seconds or a minute
right. Okay.
for people, because everyone is loading their wells, and it's 13 wells.
Makes sense.
So it takes a little bit.
Randomly. So hopefully you were able to upload the wells. And if you need time, please let us know in the chat. But I'm assuming by now you were able to upload all of them. I go to the reservoir limit test is the name of the well that we are going to working on, and go to PTA, please. And the PTA, click on this edit reservoir fluid composition and leave everything as is and click on save. And your phase envelope should be generated like this. We need this PVT module because throughout the PTA, we're going to use some of this information like formation volume factor, viscosity, compressibility in the analysis. Now, what I'm gonna do, I'm gonna go to production data, simply take a look at these. The only information that we see here is the bottom hole pressure. So the initial reservoir pressure is 5,000. We flowed this well for close to 42 days, and the collected bottom hole pressure. Now we're gonna please plot this bottom hole pressure in the semi-log plot and in the in the semi-log plot and in the Cartesian plot. This is actually the Cartesian plot, but if you go to the comparison plot, you can find a comparison plot in the over here. If we click on the comparison plot, and on the top right, add a plot and name the plot so you can identify it later as well. I'm gonna name my plot HB. And the two wells that we are interested is reservoir limit test 1, reservoir limit test 2. For this one, probably we need to do PTA, PVT as well. But for now, we're gonna add these two and click on add plot. So once you do that, this is a blank plot page that we see. Now we're gonna add our properties here. So if we click on edit, on the y-axis, simply type, let me confirm it here while we are plotting oil normalized, oil rate normalized pressure. Simply type oil normalized pressure. It's the first one here. And on the x-axis, this is time, make the scale to be a logarithmic scale. And once you do that, simply click on save. And then you don't see anything because you haven't selected any of these wells. Click on the reservoir limit test 1, and you should be able to see this. Switch this plot type to 2 by 2. We're gonna add another plot here as well. And in the just plot beside it, so what we did, plot 2 by 2 plots, click on edit, and on the y-axis again, plot oil rate, normalized pressure, and on the x-axis, leave it at time and make the scale, leave the scale to be linear. Save it. This is what we are seeing here, right? I'm gonna do a little bit of editing here. So if you press Control and click on one of these data point, or you can also do it from here. You can edit, change colors. I believe this is the one. No, not the customer. Yes, this is the change layout and design. Yes. So for the line, I'm gonna leave it to be no line. It's all your preference at this point. For the marker size, I'm gonna make it 2 and click on save. So this is my data. And now I'm gonna add the reservoir limit test 2. This is reservoir limit test. So the color are so close to each other. So I'm gonna go here and change color and spread colors. And so the color are no distinct. And what I'm gonna do, I'm gonna spread these colors and marker size over to this plot. The way that you can do it, go to change color and synchronize and color and line and marker size. So click on that. So what we generated here is the Q over delta P, why we plotted, delta P over Q, why we plot delta P over Q, simply because the equation here is delta P and there's a Q here, right? So this is delta P over Q. It's the left-hand side of the equation. The right-hand side of the equation is time, one on logarithmic scale, the other one on the Cartesian scale. So this is basically these two equations that I'm plotting here, right? And we generated this data for 2 wells. These are referred as a reservoir limit test. This is essentially they try to produce the reservoir at constant rate for extended period of time and plot the data in this way. And what I'm gonna do, I see the response too fast, so I try to slow down a little bit. So what I'm gonna do, I just simply expand this plot over here, and we're gonna see if this is actually this part of the data before it start to curve upward. Is it a straight line or is it simply a curvature that we cannot see that?
Hamid?
Yes, sir.
Do you mind just repeating the steps
Absolutely.
of how you create the comparison plot, like so that yeah,
Absolutely.
just at least very very quickly, but at least so
Absolutely.
people can see what you added in each of the axes and stuff.
So once you go to the comparison plot, right, you end up being here in this page here, and you can add a plot. Click on add a plot, and for now we can simply select 2 of our wells that we are interested: reservoir limit test 1 and reservoir limit test 2, and click on add plot. So again, add plot, select the wells of interest, and you end up being over here, right? So these are the 2 wells that we selected, and we are interested to plot a 2 by 2 plot. This is the interface. In the first plot, click on edit, and over here, type in on this is the y axis data. Type in oil rate normalized pressure. So if you type in oil rate normalized pressure, it's going to show up. On the x axis, we're going to leave it time, but we're going to plot this on the logarithmic scale. click save. And if I select my well, now it's going to show up. Select the other well, it's going to show up as well, right? This is essentially what we did. On the next plot, beside it, we're going to plot the same parameter, oil, normalized pressure. And for the x-axis, we're going to leave it as time, click on save, and this is what we're going to see. The rest of the data, it was all the cosmetic that I did. Right? I adjusted these data and the color and the shape of the marker, etc., etc. Yes.
Excuse me, can you tell me how did you get 4 different plots?
Four different plots. Say on the plot type, there's a 2x2 plot, right?
Oh, okay, thank you.
Yes.
Sorry.
I just wanted to present them side by side, and so you can see different scale. What you remember in the first one of the slides I presented was all about plotting the data in different formats, so you will be able to identify a slope, a straight line, because we love a straight line. Right? This is the premise of presenting this data in different format, so we can identify slope early time, late time, and this is the intent of this exercise actually. So let's move ahead and go to my own plot. So I color coded this. If I click on expand, now it's on a max. I want to see if the early time data, how the slope will look like. Over here, there's a slope icon. If you click on the slope, and you will be able to add a custom slope here. If you click on the custom slope, you can name your custom slope semilog, I will call it semilog, and click on save. And now I can adjust the slope of the line. So I see my data are presenting themselves on the straight line or not. It sounds like a good chunk of the data until one day, these data are presenting themselves on the straight line based on at least on this straight line over here. Going to the next line, next plot over here, if I maximize it, I'm gonna focus on this purple marker, and I'm gonna add the slope, again, custom slope, and I see late time data also presenting themselves on a straight line, but in the Cartesian plot, not in the log-log plot, right? By looking at these equations, you see that the early time data is a function of simply a log time. That's why early time data are presenting themselves on the log-log plot will present themselves on a straight line. Late time data, however, on the Cartesian plot, because it's a function of time here, presenting themselves as a straight line. So this is what we call as the reservoir limit test, and we were able to identify where the departure from the straight line is happening. The departure from a straight line, so this part of the data is dominated by, described by this equation. The late time of the data, which I presented over here, is described by this equation. Somewhere in the middle, this equation lose its credibility, and this equation will take over. So these are the data that we plot, and we identify the time, the transition from transient to boundary dominated flow, right? For the one of the wells, and for the other well, it was occurring earlier in time. If I have two more wells, one of the wells that have a smaller size, I'm expecting my data to start to deviate from the straight line earlier, and the slope for the line also to be steeper as well. And if I have another reservoir, which is also smaller in size, I'm expecting my data to deviate also earlier, and with the slope to be also steeper. So these are the time to end of linear flow, not end of linear flow, but end of transient flow, right? Where I have to use the other equation to be able to describe the rest of the data. By this, I want to introduce the radius of investigation. Radius of investigation, again, this is the vertical wall in a radial reservoir. And when we start to produce from the wellbore, actually we start to see how the pressure is propagating inside the reservoir, and this is at early time and the later time. It's very similar to how the waves how the ripples are propagating in a pond. At some point, I'm going to touch the boundary, and this at this time where the pressure is propagating, there's a location in the reservoir that the pressure has just arrived. That's the definition of radius of investigation, right? As the time goes by, the radius of investigation also will be growing by time, and at some point it reaches to the end of the reservoir. And by this, I'm going to introduce this radius of investigation, and this is the equation that we can find from simply setting these two equations equal to each other. Remember, I talked about the early time solution and late time solution. This applies to early time, this applies to late time. If we set Pi minus Pw from both sides of the equation to the same, so basically, and do some mathematical manipulation, we can I can find a relationship for the distance of investigation here. So let's revisit this equation. This is a square root under a square root. There's a permeability, there's a time, there is some porosity value. These are the rock properties, permeability and porosity, and also there are PVT properties, viscosity and compressibility. So it's very interesting that the radius of investigation in radial flow is proportional to the square root of permeability. So if you multiply the permeability by a factor of 4, the speed the wave is propagating in the reservoir is only multiplied by a factor of 2, not by a factor of 4, right? Very interesting to also revisit these parameters. So at some point, if I can identify what point in time my radius of investigation reached the boundary, then I can plug it here, and I call that time to be the time to pseudo steady state, then I can calculate the radius of the reservoir. This radius of reservoir corresponds to the time that the pressure waves arrive at the boundary of the reservoir. And then I can translate that radius of reservoir to a drainage area. So this is another way to calculate the size of the reservoir simply by plotting my data this way and try to find the time at which the data start to deviate from a straight line. This is very, very similar to the rate transient analysis work with the time to end of linear flow, if you guys have some experience in multi-frac horizontal well. And that's very similar to that. I want to take the opportunity to also present you one more feature that we recently implemented in the software. And that's if you go to the analytical OTA, you don't necessarily need to follow me. Just going to quickly present that to you. So in the analytical RTA, for the same well that we studied, reservoir limit test 1, if you go to type curve, this type curve is basically another way, it's not in the world of PTA, it's mostly in the world of RTA, but these type curves also fundamentally it's very similar to the way that we do RTA, but it also will be able to it's developed for conventional reservoir with a vertical wall in the middle of a horizontal with a vertical wall in the middle of a circular size reservoir. And this is the same data that I'm plotting Q over delta P versus some sort of material balance time. And I can quickly show you with the derivative. We're going to talk about the derivative throughout the course as well. This is also giving me the size of the reservoir as well as the permeability if I'm trying to find the stem of the data that match my match the data itself. In this case, I guess the 500. Adjust my line a little bit more, and this is a new feature that we included in the type curve word, and it's very complementary to the PTA as well. All good. So let's proceed. We talked about the radius of investigation. We plotted the data, pressure data differently, and in the log scale, in the Cartesian scale, and we come up with this one way to estimate the drainage area of the reservoir. A very interesting part of these, the distance of investigation, is doesn't depend on rate at all. So next time that you see you go to a pond, if you throw a small rock in the middle of a pond versus a big chunk of rock, in both cases the waves propagate at the same speed. It's only the magnitude of the wave amplitude that will be different. But the wave speed through those media is very identical, very the same. It's a little bit counterintuitive, but at least from the radius of investigation formulation, there is no rate here. It's only the speed at which the pressure propagates in the medium in the reservoir is only function of permeability and porosity and some PVT properties. And a critical element to this PTA is also a skin effect. We cannot, if we are dealing with any PTA data, in any build-up data, we need to deal with the skin effect as well. In terms of the skin effect, we talk about damage and stimulation. Damage means, okay, we can, with the damage, I shortlisted some reason why damage can take place and with the stimulation as well. So mathematically, how we deal with the skin effect is a vertical wall in the middle of horizontal reservoir, in the middle of extensive radial reservoir. The permeability of the reservoir is the constant permeability K. And at some point in time, we produce from this reservoir, this is how the pressure propagates into the reservoir. Right? It's inevitable that while we are drilling the well, there's going to be some mud invasion. There's going to be some fine migration. There's going to be, at some point, we're going to do some acid assimilation. We're going to do some hydraulic fracturing. So the area close to the vicinity of the wellbore going to be impacted. And that area, we're going to assign it a permeability different from the matrix permeability. It's a permeability K sub S, indicating permeability due to a skin. And that altered zone around the wellbore, we're gonna define a radius of a skin as well. So if we modify our homogeneous reservoir, which is intact, by this configuration of radius of RS and permeability, adjusted permeability, then if this permeability is higher than the matrix permeability, the pressure profile in the vicinity of the wellbore is going to be elevated. If this permeability is lower, the pressure going to be much lower than the ideal pressure profile. So by definition, a skin is any deviation from ideality. So a skin factor is a near wellbore permeability alteration. If a skin is positive, it means that higher pressure drop. The pressure drop is more than what we are expecting. This is simply because mud invasion, or because fine migration, or because swelling of the clays. If a skin is negative, then they're going to be dealing with the lower pressure. This is what we are favoring for. This is why we do acidizing, or we do a small fracture. In terms of how much pressure drop will be due to a skin factor, this is a simple formulation that we're going to talk about. It definitely depends on the rate. So if you flow your well at a higher rate, the pressure due to a skin is going to be much more as well. If your matrix permeability is lower, the flow due to a skin is going to be more as well. And in terms of mathematical formulation, this is it depends on the permeability of the skin zone and also the radius of the skin. Let's move on. This seems to be a little bit complicated because at the same time, we need to deal with permeability of the skin zone as well as the radius of the skin zone. Therefore, to simplify this, we're going to deal with the original reservoir configuration that we had, i.e., we're going to have the same permeability all across from wellbore to the radius of the external radius of the reservoir. But to account for this alteration of permeability and invaded zone, I'm going to adjust my radius of the reservoir. So instead of dealing with the actual radius of that I drilled the well for, I'm going to deal with apparent radius of the reservoir. And how this apparent radius of the reservoir will be correlated to the permeability of the skin, etc., etc. This is the equation that I presented here, right? So if you manipulate this equation, make this reservoir in such a way that instead of dealing with the actual reservoir, radius of the reservoir, the radius of the well, we deal with the apparent radius of the wellbore. And in a very simple word, if your apparent radius is bigger than radius of the wellbore, then it is a stimulated well. It makes sense, right? If you drill your wellbore with a bigger drilling bits, i.e. your apparent well is higher than your radius of well, you're going to deal with lower pressure drop in the sand face, and vice versa. If your skin is higher than is positive, indicating a damage, your apparent wellbore radius is less than. It sounds as if that well has constant permeability across the reservoir, but the well is drilled with a lower radius. So this is the skin effect. This is the pressure across due to a skin effect. How are we going to integrate it into our early time solution? Simply say delta P is here, delta P is here. We're going to add this delta P to this one, and it's going to be simplified as a plus 0.87 skin inside the parentheses. The late time solution, this is without the skin. I'm going to add this one. Let's add the same constant and multipliers here. So a skin going to be added inside the parentheses. So with a skin factor, a skin positive means damage, a skin negative means stimulation. And what's the range of a skin that we are dealing with? A skin positive could be as high as 100. In very extreme cases, where I'm going to present one example to you that what does extreme case permeability means for the CO2 injection well. And the lowest skin that you can get is the order of -6. So you see there's a contrast. Is on the positive side, you can go as high as 100. On the negative side, you can go as low as -6. And the reason for that, if you there's a limit to this parameter here. So for ln of RE divided by RW, take some typical number for RE, put it 1,000 feet. For RW, put it 0.25. Then do this calculation and see the high end of these values over here is 8. If you subtract -6, that's going to be very, so definitely this number cannot be negative. So this is how a negative skin is limited for. So with the skin effect, this is the actual valve for the CO2 injection valve. And what you see on this plot, on the x-axis time, on the y-axis, they have injectivity and flow rate. So the flow rate is in green, and the injectivity, the way they calculate it is simply they calculate a Q over P injection minus P initial. And you see at some point in time, there's a drastic change in the injectivity of the valve. So by the time they started operation at 2015, in 5 years, their injectivity dropped from 100 all the way to 20. So they are losing 80% of their injectivity simply because a phenomenon that's very common in CO2 injection valve. This is the perforation. This is a snapshot of the perforation. And this used to be a perforation, but now there's a halide precipitation that's basically clogging this perforation. And they do a multiple build-up test in between to calculate what's the skin due to this halide precipitation. And this is the plot of the skin that they come up with. So in 5 years, the skin developed from almost zero because there was no halide precipitation all the way to 100, 140 after 5 years of operation. So with the skin, we definitely have some solution because we can get rid of those skin by properly designing acidizing job. But definitely there are some costs associated with that as well. I wonder if there is any question before proceeding to the next topic, which is wellbore dynamic, or if there's any question in the chat that I'm sure some of them have been addressed, but if I'm missing anything, please let me know so I can address them before proceeding to the wellbore dynamic. Sounds like we're in a good shape here.
I think there was a question in the chat, Hamid.
Yes. There's a
about shutting in
question.
the well.
Okay, how to obtain wellbore storage from PTA? So how do we obtain wellbore storage? This is a topic that I'm going to cover right now with the wellbore storage. But wellbore storage by itself, the information on the wellbore storage is not very useful to us. But what's very useful to us and we should identify is when the wellbore storage period is finished. The effect of wellbore storage is diminished. So that's something that we need to know because all the focus of PTA is to extract reservoir properties rather than the wellbore properties. With the wellbore properties, we know how was the size of the wellbore, the fluid that's sitting in the wellbore. With the reservoir, we need to identify the permeability and the skin. Why this wellbore storage parameter is important? Because if it is a significantly big number, it can definitely influence the entire test, and we wouldn't be able to get any meaningful information out of the test simply because we didn't extend the test for a long period of time to get beyond the effect of wellbore storage. That's why it is important. But in terms of the number and translating those into number, that's not a very important parameter to obtain. Okay, so let's proceed with the wellbore storage, wellbore dynamics, and I'm going to present this one, and then we're going to take a break, and then we proceed with the rest of the, mostly spend some time on the example side as well. So on the wellbore storage, like very similar to a skin, when we do the drilling, we can't get around mud invasion. Mud invasion gonna happen. If there's an incompatibility of the water that we are injecting for the injection flow of test, the injection fluid, if it is incompatible with the mineral in the reservoir, they're gonna be clay swelling. So there's something that we inevitably are gonna deal with. Similar to a skin, the wellbore storage part is also something that we have to deal with. We need to identify it, and we need to, before doing any analysis on the data, we need to get rid of this wellbore dynamic side. And under wellbore dynamic, there are 4 categories. One of them is wellbore storage. This is the most dominant one. The other one is phase redistribution and liquid past the recorder, and also recording effect. For all of these, I try to provide some examples so you have some idea about what each of these mean. So let's move on. And this is a typical examples of how we operate the valve during a drawdown test, and going to also present during what happened in the build-up test as well. But usually we have a tubing in the valve bore. There's a packer at the end of the tubing, and when we start to open valve on the surface, the first fluid that will contribute to production is the fluid that's sitting inside the valve bore itself. So the bigger the size of the valve bore, the more the fluid that contribute from the valve bore itself. So until the pressure start to propagate from the valve bore itself to the to the perforation side, the reservoir wouldn't be contributing. And this is what we demonstrate in this plot. So on the y-axis, this is the Q that we get from the surface flow rate. We try to operate at constant flow rate. And on the y this time, on the x this time. And this red line shows the contribution from the reservoir side. So in the early time, the contribution from the reservoir is zero, is minimal, right? Simply because the fluid inside the wellbore is expanding and is fluid expansion inside the wellbore. If it is gas, going to be more expansion simply because gas has more compressibility. If it is oil, then the expansion going to be because of low compressibility of oil. We're going to have the contribution from the reservoir earlier. And as the time goes by, we see the contribution for a constant flow rate of the surface, the contribution from the sand phase start to goes up. And at some point, all this fluid that we get on the surface is simply coming from the reservoir. It is exactly at this point that we can start to do the analysis. Any data that we get in between is the transition from the wellbore, 100% dominated wellbore, because all the contribution is coming from the wellbore, to 100% dominated from the reservoir itself, right? So this is the wellbore storage side. And this is the transition from the wellbore dominated to reservoir dominated. And what we should do the analysis over when the reservoir is dominated. Similarly, on the build-up side, we're operating the wellbore at a constant rate, and all of a sudden we wanted to do a build-up, therefore we shut the well on the surface. But this profile shows you how we shut the well, the profile of the rate on the surface. When we shut the well on the surface, the reservoir is still contributing to flow, and there's going to be huge contribution from both oil and gas and water from the perforation inside the wellbore. That's why the pressure inside the wellbore is going up, right? So this is again the contribution that we get, and this is from the reservoir, and this is from all the still it's contributing until the contribution get to zero. And by definition, the buildup is when the rate zero at the sand face, not when the rate zero on the surface. So we need to know when these times ends, so we can start doing analysis on the wellbore storage. So this is the definition of wellbore storage, as the names imply. This is the storage, fluid storage inside the wellbore. And if we plot the data on the log plot, the tools that we are using, there's also included here is the wellbore storage. And I'm going to show you the equation as well. And the characteristic of the wellbore storage is a unit slope on both the data and the derivative. That's something that also included in the equation as well. And we're going to show that as well here. And this is the wellbore storage is simply coming from the fluid expansion and also changing liquid level. It's very interesting about the liquid level, how dynamically things is changing in the wellbore once we shut the well on the surface. So talking about this specifically with the buildup, when we shut the well in the surface, imagine this is an oil reservoir with water, oil, and gas all flowing to the surface, and we shut the well in here. If we shut the well here and conduct a static gradient test, we will be able to identify, because by the time we shut the well in, the gravity work is fade and going to segregate all the fluid. Gas going to be sitting on the top, oil going to be sitting in the middle, and water going to be sitting in the bottom. So if we conduct the static gradient right after the shutting, we will be able to see different slope of the fluid that's sitting in the wellbore, with the gas having the slowest, having the smallest gradient, and oil next, and water as having the highest gradient. But as the time goes by, still the flow is happening from the reservoir inside the wellbore. The gas and water and oil entering inside the wellbore, gas is still going up simply because it has less gravity and it's a lighter fluid, and going to be sitting on the top and still to expand. And once gas expanding, is pushing oil and water inside the reservoir. So it's very interesting in terms of the wellbore dynamic when we shut the well in. If we don't understand all of those and we're going to interpret those as a part of the reservoir response, that's not a good interpretation. That's not a valid interpretation. So during the buildup in the multi-phase domain, during the buildup, if there's a liquid in the right after we shut the well in, after 1 hour, 2 hours, maybe a day, depending on the permeability of the reservoir, all the liquid gonna disappear, gonna efflux inside the reservoir, simply because the gas is expanding and pushing those liquid inside the reservoir. So these are the equation that's essentially what it is a compressibility equation. A compressibility definition is compressibility equals 1 over volume times delta V divided by delta P. We manipulate it in terms of the rates, That's QB. Q times T is our delta T. Delta P and this compressibility is hidden inside this wellbore storage coefficient. And I'm going to talk about the flow regime identification when it comes to the flow regime section. But essentially, if I plot this data on the log plot, log of delta P versus log of delta T, you see that we're going to have a slope of 1. And that's essentially the slope of one line with the wellbore storage. If you turn on the wellbore storage, you will see a slope of line 1 will appears on the data itself. This is with the changing, another phenomenon is happening, the changing liquid level as a CO2 injection well that we did the analysis for a while ago. And in the CO2 injection well, they were injecting into a very shallow depth reservoir. The reservoir temperature was 13 degrees centigrade. It was much lower than the critical temperature of CO2. That's why we had some liquid CO2 inside the wellbore. On the y-axis, I'm plotting pressure differences. There was 2 gauges 10-meter offset each other, and we simply plot the pressure difference versus time, and we also the wellbore was equipped with the DTS as well, so we knew exactly where the liquid is sitting, because as the liquid was descending in the wellbore, some evaporation of the liquid was happening. It was causing some localized cooling. I don't want to get into that much, but essentially what was happening was liquid was descending in the wellbore, and at some point liquid passed the recorder, and it was when the top recorder started to see gas gradient. At this point, the top recorder was seeing liquid gradient. That's why it was elevated over here. By the time the liquid passed the top recorder, we see a distinct trend, change in the trend. And once the liquid reached to the bottom of this recorder, again, the pressure difference now is between the 2 gauges is a gas gradient rather than to be a liquid gradient over here. And at some point, the liquid disappear in the wellbore. This is all the wellbore dynamic that I mentioned during the shut-in period. And in all of these, I shouldn't do any of analysis of the gauges. The one that I should do analysis based on is the bottom hole pressure across the midpoint of perforation. So it's really important for us to be aware of the wellbore schematic. We always should be sketch the wellbore schematic. If there's a tubing in the wellbore or not, if there's a liquid in the wellbore or not, I don't care about where the recorder is telling me. I only care about how converting from this recording to the midpoint of perforation. That's really what really matters. So if there's a liquid in the wellbore, I should be able, this is what the gauge is reading. You see this anomaly. That's why I'm very interested to plot my data in terms of pressure versus time on the Cartesian plot. But what really matters is not the gauge pressure. What really matters is the sand phase pressure. So during this time, when the liquid is above the gauge, I can get the gauge reading, convert it to the bottom hole using a liquid gradient. But once the liquid passed the gauge, I should get the gauge reading. I should know the distance so I can use the gas gradient, and beyond that, I have to use the liquid gradient. That's how I'm correcting from the gauge pressure to the sand phase pressure, which therefore we use this sand phase pressure for our interpretation. Next one, it's always important to get a wellbore schematic. This is a very nice example that we're going to go through as well. This is a multi-frac horizontal well dry gas reservoir, and it's very important to be aware of where the tubing landed inside this wellbore, because there's no gauge pressure here. But what we're going to do, we're going to use the quiet side casing pressure and convert it to the bottom hole. But it's really important to know what's the end of tubing, and we're gonna deal with that when it comes to. And changing liquid level. So there's another issue. We could be simply the gauge malfunction during our recording. So this example is they conducted a static gradient prior to drawdown test, and they come up with a very good estimate of initial pressure. But when they draw down and build it up, they find out, well, the buildup plateaued at pressure lower than initial reservoir pressure. So is it really depletion, or could be the gauge malfunctioning? So when they realize, oh, well, the gauge was not recording the right number, because that definitely have some economic decision on how to develop this field or not, right? If it is very small reservoir that after only 20 days of production, we deal with 20% depletion, that's not definitely economical field to develop. Understanding what's really going at the midpoint of perforation is the critical key parameter here. And the other part is the phase redistribution, is simply because right after the shut-in, the gas is going to be here and suddenly goes all the way to the top of the wellbore, and that can screw the data, the quality of the data. That's what we call as a phase redistribution. But all in all, what I'm trying to say is that wellbore dynamics is important. We need to know how to identify them. We need to know what's the level of their strengths, because that's gonna mask the reservoir performance. If the wellbore storage is quite dominant, you're gonna mask the reservoir performance. At the end of the day, we are interested in reservoir performance, not the wellbore performance. How significant it is in the vertical well versus horizontal well? I believe horizontal well is going to be more significant simply because there are more fluid inside in the wellbore. How it is significant versus horizontal well versus multi-frac horizontal well. Multi-frac horizontal well going to be much more, because the volume of the fracture will be added to the volume of wellbore as well, right? And you can do a back of envelope calculation. How many number of fractures do you have? What's XF? What is the thickness of, what is the height of these fractures? And you can assign some number for the porosity and the thickness of reservoir, a quarter of inch, maybe smaller than that. And what you realize for 400 number of fractures, that's definitely a big number that will add up to the size of the volume of the wellbore as well. So your wellbore storage will be more pronounced as well. I'm gonna also provide two examples there, and for the wellbore storage multi-frac horizontal well. So stay tuned for that. If there is no question, I would like to offer maybe 10 minutes break or 12 minutes break. It's 9:24, it's 10:24. So maybe we get back here. Maybe it's, I don't know, 13 minutes, 14 minutes. But I would be happy to take any question if there is any. If not, please enjoy your break, and we'll see you in maybe 15 minutes. It's good. I'll take a look at the chat, and if there's any other question, I will try to address those as well. Hello again. Hopefully everyone enjoy their break. If we can resume the course here again, and there are a couple of questions here. One of them is pretty much similar, I believe. Is there a rule of thumb for how much production before shutting in the well to add when analyzing a buildup? That's a very good question. I believe this question coming from our clients at the conventional world. One of the main reasons why we do PTA to come up with the average reservoir pressure, right? With the average reservoir pressure in the unconventional world, milliliter non-adversary permeability, it takes forever for the pressure to build up. So that's why PTA has most of its value in the conventional world to come up with the estimate of average reservoir pressure, permeability in the skin, and the pressure build up so quickly in those words that we don't need to shut the well in for a month before we get a meaningful result. In the multi-frac horizontal well with the nanodorsal permeability, that's not the case. But to address this question, we're gonna also deep dive a little bit. Is there a rule of thumb for how long do we need the production before shutting in the well? You remember the distance of investigation? We talked about the time where how long would it take for the pressure propagate in some certain distance. So you can work this equation backward if you're going to have some idea about if you have an observation well sitting like let's say 1,000 feet apart from your operational well, your producing well, and you're going to set the well on production. You want to see how long would it take for that observation well, which now serving as there's a gauge in the bottom hole, so you can measure the pressure down hole. You have the distance from the producing well, you have the PVD property, permeability, and porosity. This is how long would it take in terms of the time for the pressure to propagate inside the wellbore, inside the reservoir. This radius of investigation is traditionally developed for the drawdown test. For the build-up test, we also deal with the radius of investigation. But the radius of investigation for the buildup is a little bit different. The way we treat the radius of investigation in the buildup is this equation here, which I'm going to walk you through this equation, by the way. It's a very simple equation. They call it delta T effective time. It is how long would it take for the pressure to propagate in the buildup test. And you see the time a function of TP, delta T, and TP plus delta P over in the denominator. So so if you ask, I want to reward this question. I put it this way. If you produce for 1 hour and you shut the well in for 1 month, would you distance of investigation will be equal to 1 month or would be equal to 1 hour? So that's a critical question to answer, right? And we can address that question through this delta T equivalent. So if we increase delta T by a lot, So delta t plus Tp is essentially become delta t because delta t is no large number, and Tp plus delta t, Tp times delta p, and we're going to be simplified by delta t. So at the end of the day, what we remaining in Tp. So what does it telling me? The distance of investigation during buildup, the high end of that, the maximum value for that would be equal to Tp, simply by taking a look at this equation. So if, if you wait for 1 month, the maximum of investigated area will be equal to TP, which is only 1 hour. So essentially, the distance of investigation during buildup is capped by distance of investigation during the drawdown. So if you're going to see a fault that's sitting, let's say, 1,000 feet apart from your producing well, and you only produce for 1 hour, there's no way that you can get the signal during the buildup as well. So the rule of thumb, how much production, if you're producing for 1 month, the maximum investigated area that you can get from the buildup is 1 month as well. So hopefully that somehow answers the question. And with that, I guess both of these are very similar questions. Recommend shutting, yeah, all good. Okay, let's talk about quickly about the superposition. That would be very simple concept. It's not that simple, but I try to make it a very simplified. It's talking about the superposition, because in the superposition world, this is the actual production data and the rate and pressure that we get most of the time, right? We're going to produce it, we're going to ramp up, open the choke, and then we're going to shut the valve in for some operation, maybe gas leak, maybe compressor, whatever, and then we're going to produce it back on production. And this is the best that we can get out of our production data. And the pressure data are going to do all sort of things like here. And then we're going to do the analysis on the buildup, right? Or maybe there's a buildup here, but we're going to do the analysis on the buildup here as well, right? Well, one of the main assumptions that we had here is for the constant rate production. I'm not sure if I listed here or not, but main assumption here that we had is for constant rate production. There is the superposition principle that we are using. And with the superposition principle, we're going to use the same equation, but using a superposition approach. But for the sake of simplification, you see this constant here, this is this slope here, is simply we're going to call it m, and all of these parameters we're going to call it s prime to distinguish it from skein s. So we're going to call it this, and this will be simplified as this. So at least I'm expecting you to bear with me with this simplified equation, which is delta p m times log of t plus skein s prime, which is a combination of all of these parameters. All of these parameters, by the way, is constant because this equation is for constant rate production. Now we're going to use this equation to deal with the cases where we have rate changes, shut-ins, rate changes, resume production, shut-in again. So how to do that? A very simplified version of that would be a well is producing a plus Q for some period of time. We're going to call it TP, producing time, and then the well shut. So the well is shutting and the pressure is building up. How to treat it, this one? I'm expecting to apply this equation only for constant rate. This is a kind of a variable rate, and my second rate is essentially 0. So the way to treat these data, I'm going to copy the same configuration here, but I'm going to assume that for the time beyond TP, I'm going to call it delta T because it's the way that shows in the equations, simply T minus TP. This is very a simple terminology I'm using here. And I'm going to assume that this will continue production at the same rate at the just prior to shutting. So if this is the case, this is a constant rate production, right? But beyond TP, I'm now producing, which I shouldn't be producing. So to account for this extra production, I drill another well and start injecting instead of producing. So injection is depicted here by minus Q oil at the same value here, but with a negative sign, now injecting. So the beauty of this is that this will start to produce to get to be on production or injection after TP for delta T amount of time, but still it is a constant rate. So I'm dealing, instead of dealing with one rate with changing rate, one well with changing rate, I'm dealing with two distinct wells. Each of them are producing at constant rate, but they come on production or injection at different time. Now I can apply that equation because that equation is developed for constant rate production. So let's apply that equation to this configuration. This is my well. This is well 1, well 2. I'm going to apply that equation for both of these wells, right? This is my equation, m log of t plus s prime. For the top well, this is delta p plus q, is m log of t plus delta t. This is the producing time. Now it had been producing on production TP plus all these delta T over here, plus S prime. delta P negative is Q for the injection part is simply minus, simply because we are injecting, the pressure goes up. So we account for that by this minus M times log. How long has it been on production? Delta T. It hasn't been on production since time 0. So it has been on production since time delta T time, right? And simply we can add up delta pressure inside. Add them up and equal to, this is the logarithmic feature that we can add them up and show that on here. What is this PWS? This is the PW shut, because we are analyzing the shut-in profile, right? The pressure is building up. And what do we call this time? Is we call it Horner time. So as simple as that. For the build-up, we simply superimpose two solutions, one for continued production and one for injection valve that comes on production after any rate change. I can repeat this practice for any number of well change or rate changes that I'm dealing with. So if there's a rate change here, I can introduce another valve. If there's a rate change, I can introduce another valve. Any of these rate changes, I can account with bringing another valve either on production or on injection, depending on how the rate is changing, right? So with that, define a superposition time function. This superposition, we call it Horner time, we call it a superposition time function, and the way that we develop, we utilize this equation to come up with that superposition time function. We call it Horner time. A very simplified approach that we implement in the software as well is to assume all this rate history, it produces at a constant rate. And we define TP to be a cumulative of production divided by Q, last Q. This equation, we are also familiar in the rate transient analysis board, in the RTA board, when we do the square root of time plot. There's a time function that we call it is a material balance time function. That's essentially, this is a material balance time function. So a very simplified version of this multi-rate approach is to account is a constant rate. What that constant rate is simply cumulative production divided by last Q. That's what we call it TP, and we're going to utilize it in the equation. So for the build-up, this is the equation that we're going to use. And if you plot the data on the semi-log plot, this is TP plus delta T, TP plus delta P. This is a log, therefore this is a x-axis, is a logarithmic, and what we plot on the y-axis is simply PW short. And you see, if I start with a very low delta T and then start to progress in time, my TP plus delta T divided by delta T will increase in this direction, right? So if I plot my data, you're gonna deal with some data with the increasing shut-in time in this direction. If you send delta T to 1000 and TP is simply 1, 1000 divided by 1000 is 1, and 1 is over here. So the number is increasing this way. But most of the time, people are more comfortable with increasing the shut-in time in this way. So they reverse the x-axis, and instead of increasing this way, they put it in this way. So the time is increasing this way, but my Horner time is increasing this way, right? So basically the same data set, but it flipped. Simply just people are more comfortable with looking at increasing time in this direction rather than in this direction. So build-up analysis, again, there's a question here that what happened to a skin, right? Why there is no skin? Because simply a skin canceled when I sum up these two numbers, these two parameters over here. So this skin and this skin, for the positive and negative skin, they cancel out because there's a negative sign sitting here. So does it mean that during the build-up, there is no pressure due to a skin? Anybody wanted to give it a shot? During shut-in time, essentially the skin will cancel out. They cancel out simply by adding these two equations. And what it means is that there's no delta P due to a skin. It makes sense intuitively because when we shut the valve in, what's the rate? Rate is 0 essentially, right? With the rate 0, the equation for a skin, go to the equation for a skin. If you remember, this is the equation for the skin. Delta P is, there's a Q component sitting here. With the rate equal to 0, delta P due to a skin is 0. But is there any way, does it mean that we cannot calculate a skin during the shut-in? Of course we can, and the way to do it is using the data just prior to shut-in, where the well is still flowing, is the PWF, and this is the time where we started. Essentially, it is the TP time, right? At the TP time, there's a skin parameter here. So this is one single point prior to shut-in, and after TP, the well is shut in, so the pressure is building up. But this last data point, there's a skin parameter here. So if I sum these two up, this equation, I come up with this equation, a simple manipulation of logs. It's going to be TP delta T, TP plus delta T, and there's a skin. So I can calculate a skin utilizing the last data point prior to shutting. That's what essentially it is. All good. So what we call this one, this is time delta time effective. And what's telling me, it gives me some idea about how the pressure is propagating during the build-up time. And we can utilize this time function very similar to the time function that we use during the drawdown. And all the assumption that we made so far are for the oil well, for the gas well. However, we simply use pseudo pressure and pseudo time. And what is pseudo pressure? It's simply transformation of the this kind of transformation. We know for oil, viscosity and formation volume factor is fairly constant for the pressure range that we are operating. For a gas, however, these two parameters are changing drastically. In order to be able to utilize oil equation, but for gas, we define pseudo pressure. This is the definition of pseudo pressure, and simply we replace anywhere in the equation of oil, if we see pressure, we replace it by pseudo pressure. And the other transformation that we need to do is the pseudo time. It's a little bit in terms of the math and how it is calculated. You don't need to learn all of those, but it is important for you to be familiar with all of those, because in the software we specify that for the gas, when you pick your phase to be gas for analysis, all the time function will be transformed into pseudo time domain, and all the pressure function, all the pressure parameter will be transformed into pseudo pressure domain. So these are two simple modifications that we need to do for the gas. Let's quickly talk about the flow regime. Maybe we can do one example here prior to this. So we can go now to the examples. Okay, so if you go to the valves, and gonna go to one of the valves that says the wellbore storage boundary, WBS boundary. So in the valves, if you go to wellbore storage, if I'm fast on navigating into the software, please let me know so I can tune my pace. That would be really helpful. So in the PVT section, if we go to the PVT section, we definitely need PVT to do any PTA analysis. PTA analysis, that's not the correct word to perform any PTA. And we need to edit on the reservoir properties and leave all the parameter as is and click on save. And once you do that, you end up with a phase envelope. And that's all we need to do here. And then deploy a fix last night, but we reverted back because it caused some other issue. What an extra step we should take is to go to production data. And in the production data, click on edit. And once you click on edit, scroll down. Second column is Q oil. And at some point, you see a blank cell, and you need to fill that blank cell 0. So this indicates that your build-up started at this point. So this time, this is my TP, essentially. This is my TP, this is my producing time. 4.17 days is my producing time. And this number minus this number is my delta T, right? This number minus this number is my delta T. So what I need to do is fill all these blank cells with zeros all the way to the end. I have already did this during the break. So you need to type in 0, and then you can go to the edge of the cell, and you see this plus sign shows up, very similar to Excel. You need to drag it downward all the way to the last data point, and this is my build-up period. Now click on save, and my data show up like this. So this is drawdown, this is build-up, and you can zoom in on how the pressure is building up, right? So by looking at this data, I can easily confirm that this is my initial reservoir pressure. This is my average reservoir pressure, 4903. If I'm collecting the right bottom hole pressure at the midpoint of perforation, right? So I started at initial reservoir pressure 5,000, produced for a while. This is a small reservoir for sure. And then I build it up. I'm interested to do some build-up analysis. And I see that the pressure plateaued here. So it will be very insightful to see how the derivative will look like for the because flat line indicating the derivative is 0, right? But at the same time, it will be interested to take a look at the permeability and other information that we can get, or if there is an available storage. But the intent of this exercise, as the name is implies, we are able to identify the boundary. We should be able to identify the boundary simply by looking at the raw data here. As the pressure plateaued and the pressure is not building up, it's indicating that I'm draining from a volumetric reservoir. And during the early time, I'm interested in available storage. So once you edited your production data the way I mentioned to you by filling up these cells by 0, you can go to well test. Under well test, there's a PTA. So if you see something like this, you need to expand the drop-down list and click on the PTA. And once you click on the PTA, this is the interface, the first time interface that you're seeing here. So we have good chunk of time here to invest on these and explore all the options that we can get. Let's walk you through the interface first. So the first thing that you need to do is to say, what part of the data would you like to see? So let me show you quickly one of the functionality that I have here. And this is for a different valve. So you don't need to follow this, by the way. I just want to put it for the demonstration purposes. There's a one valve that's radial oil multi-valve buildup. So I need to go to PVT and very similar PVT and in the production data. I'm glad this production data is filled already with zeros. No, okay, I have to fill it. I mean, set it to 0. And there's another period of buildup. And this is the second build-up. The reason why I'm interested to show this to you is the capability of the software if there are multiple build-up. Why there are multiple build-up? Because simply people do different stimulation strategy. At some point they do acidizing, they're gonna see how effective that acidizing job has been. Therefore, they're gonna do a build-up and come up with a skin value, which is tend to be negative. Hopefully this is negative, not positive, because the test is not properly designed. And next year, 2 years from now, they're going to do the same acidizing job. So if their skin is -2, they're going to do another acidizing job, see if they can bump it up to -3. So that's why they design another build-up test. So the software should be able to analyze any build-up test, right? Any number of build-up tests. So I'm gonna set them to 0. The reason why we need to import this as 0 is simply because the way that the PTA module is set up for the truncation feature that I'm gonna show to you is identify the build-up period for those period that the rate is 0. That's how the truncation feature is functioning right now. So let's say this is the entire production data, right? With the entire production data, I'm going to leave this aside for now. And there's a period of build-up, flow, and build-up. So this is the first acidizing job, the second period of flow, and second acidizing job, and maybe third acidizing job. And you're interested to see, analyze each of the skin and permeability. Maybe your permeability degraded because it's a pressure-sensitive formation. If it is pressure-sensitive formation and the permeability drop start to decline from 1 millidarcy to 0.1 millidarcy, that's a good indication that, yeah, the sensitivity works here. So that's one way that you can have a series of build-up and do the analysis on all of them and then compare the results. So if you're going to focus on the early time data, early time build-up, there's two lines, black line and blue line, that you need to utilize in order to identify which period of build-up you want to do. The only thing that you need to do is to leave this black dash line prior to shut-in period. And with the blue line, just leave it somewhere here, just prior to the next build-up. You can always zoom in and fine-tune all of these if you want to include this data point, if you are happy with all of your data point. If there's any other activity, for instance, a nearby well, and this data is impacted by that, then you're going to leave this data over here, right? You don't want to ignore all of this data. But we will be including a lot of features like filtering, so you can identify visually bad data from the good data. And if you leave it like that and truncate, you see now only the data will include in the first shutting is used for interpretation, right? And so this is my initial analysis of the data. And if I'm going to do the analysis on this, you see there's an early part data is there's available storage line, which this data, if you remember the equation on the log plot should be unit slope. And this line is actually a unit slope. And you can confirm it by just making a square and set it to the edge of a square and find out this is a unit slope. So this is the unit slope. The best practice to get beyond the well-bore storage is where you see the data is start to terminate and deviate from a straight line. You go beyond those data 1.5 log cycle. So this is 1 log cycle. This is another half log cycle. Visually, this is where your reservoir start to contribute. If it is drawdown, the surface flow rate will be your reservoir flow rate. If it is build up, at this point, you believe the build up, the flow rate from the reservoir is zero. So this is how we identify wellbore storage and get beyond that, right? So you do your analysis based on this one. And if you want to do another analysis based on last data point, last shut-in point, all the thing that you need to do is to move this one, truncate this chunk of the data. And you can always zoom in and confirm that you're happy with this and do this truncation. You know this part of the data is selected for analysis. So you can use any build-up number of build-up data that you have. There's also this truncation. So essentially, these two fields deal with truncation. The next one we have is we are using oil phase for our analysis, or we are using gas well. So all of these well test equations are based on a single phase flow, oil or gas. So if you're heavily multi-phase, there are always, you need to take your interpretation with a grain of salt. If it is single phase, yeah, you're welcome to use these. And in the analysis, we're going to talk about this linear, bilinear, and radial. Why radial is grayed out? Because let's talk about these two plots over here as well. Before that, I'm going to talk about this bottom plot, which is we call it a type curve, simply because type curve are plotted delta P versus time, some sort of time function, which is on the log-log plot, simply because it's a log-log plot. It's helped us with the derivative analysis, and we're going to talk about the derivative analysis, and these are all the slope that we have for the derivative. We're going to talk about that. And there's a button here, there's a time function. What time function do we need to use here? The first time function is simply time, is the actual time, right? It is very similar to here, but here is a Cartesian, this is a log-log plot. The other one is the radial equivalent, and we have two time function for each of these flow regime. The first one is equivalent, the other one is superposition radial equivalent. We're going to talk about those. First, let me introduce these two plot. Over here is basically because this fundamentally is designed for the drawdown and build up, and because it's a build up, therefore we have a Horner time. What is a Horner time? We just introduced Horner time in over here. This is a Horner time. And if TP is simply by this definition, we call it a Horner time. If TP is simply, if we accounted for all the rate changes, so anytime that the rate change is happening, which essentially every day the rate is changing, we are not preserving rate at a constant, the rate is changing smoothly. If we account for any of those rate changes, we call it a superposition that accounted for any of those rate changes. That's the Horner time, which assume all the rate changes are taken into the calculation. That's basically a superposition. What sort of superposition time function is for the linear flow geometry. I'm going to talk to that as well. But for now, let's talk to this one. It's going to be a radial flow, because my well that I generated this data is a radial flow. Therefore, I selected radial. And once I selected the radial, now I'm able to select radial as well, right? So if I selected the radial, all these parameters are changed accordingly to a radial flow as well. So this is, I don't want to do interpretation on this, but I'm going to do the interpretation on the wellbore storage, the other well that you guys also have. And so at one point in time, because we run out of space, so we decided to set it up like this. So on the right two plots, you can select between all the three flow geometry that we have. For instance, if you have a vertical well in a conventional reservoir, and the vertical well, we know the flow regime, dominant flow regime, is a radial flow regime. But if you have a multi-frac horizontal well, we definitely can have a linear flow regime. If it is finite conductivity, we can have a bilinear flow regime, right? So that's why how we selected. So if we select this one, and now I change my analysis to be a linear, all these parameters will also change correspondingly based on the linear analysis. So this is for multiple buildups, how the truncation work, what each of these basically plot means. So there's a question in the chat, if you're going to do fall off in a test, what phase should be selected? That's a very good point. So we're going to add a water phase here as well. So we'll be able to use the water. And for this, so far we included drawdown buildup. Injection fall off will be identical The only difference between the two is the negative sign. So instead of the pressure is building up, the pressure is falling off. But in terms of the interface analysis, everything gonna stay the same. So this is about this well. Let's go back to our wells and again. So if we are on the same page here. Up to this step, I'm gonna show you how to do the analysis for this one. So if I expand this plot, first thing I'm gonna do, so this is a primary pressure derivative. Let's get rid of that for now. And what we see on this page is delta P versus time on the log-log plot along with the derivative. So I'm going to expand it like this, and daily time data, as you see, is identified by a well-bore storage. So I'm going to select the well-bore storage, and I'm going to leave the well-bore storage line over my data, and I can see the departure is taking place over here. So I advance in time 1.5 log cycle. That's what people recommended based on practices. Is it coming from any textbook, like in terms of mathematics? No, it's mostly coming from the practice. So based on their experience, they recommended for the when we started to see deviation from this straight line, it will take us another log and half cycle to get beyond that. So you see, when the deviation is taking place, if the deviation is taking place after 1 day, I have to wait 10 days to get beyond well-bore storage. But what if the deviation takes place after 10 days? I have to wait 100 days and beyond that 170 days, because 1 point log cycle is not 1.5 times 100, right? Times 10. It is more than 1.7 times 10. So that's the caveat. So depending on where the deviation is taking place, if it is 1 day, I'm very comfortable to wait for 10 days. But if it is 100 days, if it is 10 days, waiting 100 days and then putting the production on hold for 150 days is a big deal, right? So that's the transition. This part of the data tell us some information about the well-bore storage. I'm sure we have that well-bore storage somewhere. Information, this is well-bore coefficient. What are you gonna do with that? I'm not 100% sure what would be the usefulness of this one. So what I know from this data, I have to advance 1.5 log cycle to be able to identify another flow regime. So we see all the analysis we do on the derivative. So let's go ahead and we know that this is a build-up data, so we need to look at some time function other than the actual time. And in this case, I'm going to select radial equivalent. Radial equivalent and superposition radial equivalent. First of all, what is equivalent? Equivalent, this is the time function that we define here. This is simply because we are also interested in the scheme. The way we develop the equation during the build-up, it can disappear simply because we sum them up, one positive, one negative. But we wanted to also know about the scheme. Otherwise, there's no point on running the build-up test. Therefore, we included the last data point just prior to shutting. Those information I know. I have a recorder in the well, therefore I know this one, and I know the TP values. Therefore, I can combine this equation and come up with this delta T equivalent. So essentially, what do we mean by equivalent? This is simply plotting this equivalent delta time here. So if I'm interested to account for all the rate changes, I use the superposition radial equivalent. If I'm only accounting for assuming this assumption, which is not a bad assumption, actually, sometimes this is a very good assumption, simply cumulative over last Q. I'm using a radial equivalent. For now, because there's only one single rate, as you see here, the rate hasn't changed. The rate has stayed flat. It's a constant rate production and then shutting. So both of those function will provide you very similar number. I have another example that will present to you where it is a different number. So the rate is changing. So using this to slightly modify the data. So using this radial equivalent, I'm going to expand it one more time. So I'm using radial equivalent for my time function. Well-bore storage is the early time. This is not the data that I can't do anything with this data in the middle. This hump, this is useless in terms of interpretation. But it's tell me when my actual well performance reservoir performance start to show up. So I'm gonna stay here with my actual. I'm gonna talk about the flow regime shortly here, but for now, let's also include a zero slope here. That will add a zero slope line. Will show you at this point here, this data point here, at least the derivative is flat, indicating that there's a reservoir performance here. And we also see a deviation from a straight line, from this horizontal line. That's where the boundary effect start to show up. And you remember, the pressure start to plateau because we are arriving at average reservoir pressure. And for the plateaued pressure profile, what's the derivative of a flat line? The derivative is zero. That's why the derivative is going to zero. And as a matter of fact, because this is a log, right? So point one is very similar to zero derivative here. So we don't not specifically plot zero because it's simply it is a log scale. So if I'm using a radial time function indicating that my flow regime is mainly a radial flow, for the flow type, I'm gonna also select a radial flow. So if it is a radial flow, early time is distorted by well-bore storage. That's the early time that I see also distorted. The middle part of the disk is presenting itself in the straight line. So I can use this fit option and straight line fit and select this data point. And you see how nicely, if I'm seeing a straight line over here, I also have a flat line. Could the bump in the derivative indicate a fracture? Could the bump in the derivative? If we are talking specifically about this bump, I would say no, because this is the transition from the well-bore storage to the reservoir contribution. Okay. So this is the well-bore storage. You show how on the log plot we are able to identify through this well-bore storage line, and also on the Horner time plot, Horner plot, we're also able to identify that the straight line. And this part of the data, where it's plateaued, is essentially average reservoir pressure. Okay. Let me quickly walk you through these, and I'm really interested to present you the actual cases that we have here. The asphalt, we talk about the asphalt. Let's talk quickly about the flow regime. We have different flow regime: well-bore storage, radial, linear, and bilinear. The radial flow regime, this is my equation, right? And this is my flow equation, drawdown. This is my buildup equation, delta T equivalent. If it is a linear flow regime, I simplified it very much, but you can find all the equation for the slope, etc., in the manual part. But what is really is the time function that we are using is a log time. The time function for the linear flow is the square root of time plot. Is the square root of time. In the shut-in, this is the Horner time plot. So it's simply because of the logarithmic of difference of logarithmic is the ratio of the parameters in the logarithmic in front of the logarithmic. But here, this is how we define the Horner time. And for bilinear, drawdown is force root of time, and this is the buildup. And lastly, for the well-bore storage, this is the equation for well-bore. So all the things that you need to know about this equation: radial is logarithmic, linear is a square root of time, bilinear is force root of time, and well-bore storage is simply a linear function of time. So the same way that we went through this equation, the derivative that we are referring to here is simply this derivative, is semi-log derivative. You don't need to calculate this complex equation here. The only thing that you need to do is to do dp divided by dt multiplied by t. This is the simple definition of the derivative. And what's telling me if my flow regime is mainly radial flow regime, if I take the derivative based on this one, t times dp dt, this is simply a slope divided by a constant. So my derivative is a constant number, and we confirm that, right? In this valve, which is this valve is I use a radial equation to develop the shut-in period for this one. You see, my derivative is flat line over here. And what is the value of this flat line? What is the actual value? If I read it from the y-axis, it relates to a slope of this line divided by 2.3. So if I make the slope steeper, so how the derivative is increasing. If I increase the derivative, also the derivative, the slope on the radial model also start to get steeper. If I reduce the intercept, my slope doesn't. My slope also gets steeper. So if I don't change the slope, but I move it away, this derivative doesn't change, because this derivative, the value of this derivative depends on the slope of the line. So if I move it over here, there, it doesn't change. But if I change the slope, it also change correspondingly. So this is how they are connected, these two. So we can do the analysis both on the derivative and on the data. Sometimes the derivative is so mess. It's a cloud of the data. You can't do anything with the data with the derivative itself, but you can do a lot. At least the trend of the data is very nicely. You can find some trends, so you can use your line to adjust and adjust it. So you believe this is the reservoir contribution, and the derivative also because it's the way it's connected to the slope through this equation will sort itself out. On the radial and the linear, so this is the linear. So if I simply take the derivative, a half a slope show up. In the bilinear, a quarter slope show up. In the Velbor storage, a unit slope show up. So let's quickly talk about this as well in the derivative. So if I add a quarter slope here, this is for the bilinear flow. Now we're going to take a look at another well. And it is, if you switch the valve to, let's take a look at to bilinear oil, the bilinear oil. So if you change your valve to bilinear oil, and the first thing first, we need to go to the PVT section. So what I did, the well section, I switched to bilinear oil, go to PVT and click on this edit button, leave as is, click on save and go to production data. So this PVT step is essential and go to production data. In the production data, what we need to do is to click on edit and scroll down all the way. So you see the first blank cell, fill it with 0. And once you fill it with 0, it's very similar to Excel functionality. We can drag it down all the way, fill all these cells and let go. So essentially, because this is the feature that truncation is using, you just can seek for the data or the timestamp that with the rate 0 and select that one to be your build-up. Click on save. And once you do that, this is my data. Now I'm going to go to the PTA section underneath well testing. In the PTA section, you see something like this, you need to refresh your page. So the correct production data will be transferred over. And the software you see automatically identify the build-up period. But if you have multiple build-up and you want to truncate it, you can use this truncated feature. For now, I'm very content with this one. So let's go here and look at the time. So you may argue, okay, what's the best time function to select here, right? The best time function to select in the first place depends on the well geometry that because we have those information. We are not given raw data and say, go analyze this when we don't have any information about the well geometry. So essentially, we know the well geometry. If it is a vertical wall, we're going to install always with the radial. If it is a multi-frac horizontal wall, we can either use a linear equivalent or bilinear equivalent, right? These are the two functions for the dominant flow regime in the multi-frac horizontal wall. For now, I'm going to start with linear. And if I'm selecting a linear, the data seems to be on the straight line very nicely, but I'm going to select a slope. So let me maximize this one. I'm going to select a slope and I'm going to add half a slope and also a quarter slope. Sometimes the slope is outside of the chart. You can go to the end of the plot and you see this double-headed arrow and squeeze it and you can find your lines, whatever. So it is, or you can go to other end of that and also you can squeeze it. So when you find your line, you move your line to the data and then double click and it will reset. So you see this data on the derivative side. So I'm going to remove the PPD as well, primary pressure derivative. And so this is my data. This is my build-up data. This is my derivative. So the derivative seems to be more close to quarter slope than half a slope. And there is no well-bore storage here. There's tiny bit of well-bore storage, so we can ignore it. We can say this is a reservoir effect. And you can clearly see the data, the derivative of the data are more aligned to a quarter slope than half a slope. So this all seems to be a finite conductivity fracture, and to be able to get the finite conductivity fracture information. So now I'm using a linear equivalent. I would better use the better time function, which is a bilinear equivalent. So what's the best practice? You need to practice both of these. And once you practice both of these, the data may not change by much if you transfer between different time functions. So at least from this interpretation of the derivative, I can see if I go to the derivative, you see if I'm bilinear, when I plot this data, when I take the log of derivative versus log of this one, this is the quarter slope line that shows up in the data, right? And how it is connected. Okay, so let's go ahead and do the analysis. I'm going to do the analysis on this side. So I'm going to select the bilinear flow regime here. And with the bilinear flow regime. I need to adjust this one. Maybe we need to a little bit be patient with this. So again, just for the sake of not making this plot busy, I'm gonna remove the Velbora storage, not much Velbora storage here. I'm also gonna remove the half slope, and this is the data. Again, the way that these two lines are connected, I can change the slope of the line. This line is always a quarter slope, but I can change it vertically, right? The location, the vertical location is very well correspond to the slope of the line. So if I make the slope of the line adjusted to my data, the derivative also shows on the derivative data. The quarter slope also shows on the derivative. This is how they are connected as well. Okay, so at your convenience, you may also investigate radial oil, linear oil, bilinear oil, and also bilinear gas, radial gas, and also we already took a look at these two reservoir limit tests, and I'm sure there's another one. There should be a linear gas. Okay, yeah, these are the 6 wells that we investigated, and this is multiple buildup. We took a look at the wellbore storage. So what we are left off with is a multi-frac oil, and this is RTA PTA. Let's quickly see what we are remain the remainder of the slide. Injection fall-off. We're going to take a look at this injection fall-off as well. We don't do analysis on this one yet, but this is what we are expecting from injection fall-off, right? We are injecting and bumping up the rate, and the pressure is also increasing accordingly. This is based on theory. This is simply based on theory, but in actual work, this is the test that was involved, and they injected into an aquifer, and the rate that they are injecting is like crazy high. It's the order of 10,000 barrel per day, bump up to 30,000 barrel per day. So we say these are 30 Ks. So they bump up the injection rate, and anytime that you see they bump up the injection rate, the pressure build up. There's no common similarity between this pressure build up and it has very immediate response, increasing and plateauing, increasing and stabilizing, increasing and stabilizing with this one, right? There are a lot of thing going on in the actual world that we conducted this test. Yes, over here, I can clearly see the pressure is increasing. You also have access to this data set, by the way, in the this is an injection fall-off test. Let's have a quick look over this one. We're gonna quickly take a look at the production data here. And okay, so this is the water rate that let me put it on the Cartesian scale. These are on the order of multi-frac drops in terms of the rate that they are injecting, and this is the flowing bottom hole pressure. This is during the injection. So you see, at some point they bump up the injection rate, but the pressure goes on the decline rather than going up. And simply, if I want to add some information here, is because simply they added some friction reducing agent to the injection water, and they clearly see that they wanted to do a multi-rate test to come up with the fracture pressure, but they somehow screw up the test by introducing those friction reducing agents that cause the pressure to go down instead of going up. But more interesting part of these is injection fall off. We don't do any analysis on the injection simply because of all the noisiness of the data, but we do the analysis on the fall of the part of the test. I'm going to quickly take a look at that data, and this is the fall of data. This is the fall of data, and you see because they didn't close the valve so quickly, this is the pressure that they inspected, and the valve also went on vacuum, indicating that it was very subnormal pressure. And the only piece of information that you can do the analysis on this profile of the fall of the data, right? So in actual world, designing a test could be as challenging as because if the test doesn't turn out to be a good test, your analysis is going to be very difficult after that. So we pretty much covered the content here in terms of the derivative flow regime, etc., etc. And I'm happy now to, for the remainder of the time, go to two examples. These are the real examples from multi-frac horizontal wall. I also had like a vertical wall, but to change the theme here, especially, I know some of the attendees are from the conventional world. They are operating conventional reservoir, so we'll be happy to include those examples for our future courses. But here, the one that I'm interested to present to you is RTA, a combination of RTA PTA test. This is if you switch to this wall RTA PTA. This is I requested the generous, a great friend of mine, generously they offered to use these data. I manipulated the data a bit in terms of the rate, preserve the characteristics of the rate that for the well that produce. In terms of the information, initial reservoir, I adjusted a little bit. So I'm gonna spend some time in doing first rate transient analysis, best practices for rate transient analysis, and then do a build up PTA analysis on this one, and then be able to compare the results that I get from the both of them, right? And what parameter specifically we are interested to compare is a linear flow parameter. This will also produce some condensate, but the amount of condensate was so low, so I safely delete those. Also produce some water. In terms of the how much water is produced is 26 STB, but the very good information that we can have in order to see where this water is coming. Is it the water that comes from the reservoir, or is it the water of condensation? So there's a rule of thumb. We take a look at the ratio, and in this case, I'm gonna take a look at water gas ratio. Water gas ratio 15. So 15, 16, you see a start a little bit high at 20, stabilize around 10, 12, something like that. So 10, 12, some of this water is the water of condensation, right? Depending on the reservoir temperature and reservoir pressure. Some of this water are evaporated in the gas phase. When they come to the surface, the gas cool down and water condensate. Now, water of condensation is could be a good portion of the water production if the reservoir temperature is so hot, because the more the temperature, the higher the temperature, the more water is evaporated in the gas phase. So that's something to keep in mind when it comes to water analysis. But you see that the rates are very smoothly declining, and it's very gentle, slow, gentle decline. And there are some slight interruption in the operation. Not exactly sure what happened. I don't know anything about the history of the well. The only thing that I know is this shut-in period. This shut-in period is extended shut-in period, has been on shut-in for over a year and a half, close to a year and a half, I would say. And what information, other information do we have? We have casing pressure and tubing pressure. Right? We don't have any bottom hole gauges, and we only have casing pressure and tubing pressure, and there's no packer in the hole. So so what in the first place, what we should do, we should convert the surface pressure to bottom hole pressure, right? And during the shut-in period, you see the tubing do very crazy stuff here. I don't believe this is very good quality data to use the tubing to convert to bottom hole pressure, right? So what I'm gonna do, I'm gonna use the casing instead. The casing pressure, you see how gently, how smoothly it is inclining, and there's a small changes between casing and tubing. At some point, the difference is 1451. It's always good to take a look at the differences between the two and do the analysis. So in the first part of this study, I'm gonna do RTA. I'm gonna perform RTA and RTA. And what I'm gonna do, I'm gonna go to PVT and edit the reservoir properties and the gas specific property 0.5 and click on save. And my PVT is now initialized. And the production data, we took a look at that. A very interesting part of these is the casing and casing and tubing pressure. So with the casing and tubing pressure, we can gain a lot of information about what really happening in terms of the mechanism in the wellbore, if the wellbore is liquid loaded or not. But the first place that I'm gonna take a look is go to bottom hole pressure, and in the bottom hole pressure, I'm gonna see the wellbore configuration. This is the well deviation survey. So with the well deviation survey, this is where the well is landed, close to 55 TBD. And I make sure the temperature and pressure is consistent here at that depth. In the well data, there's a casing, also there's a tubing that is installed from day one, and the flow pass is taking place from the tubing. In the compute through, there's a flowing side and there's a quiet side. So which one is your preference? I'm going to add some color here. For my preference, definitely I'm going to use the static quiet side. Why? Simply because comparing the tubing and casing going to get me a lot of information if the liquid loading is happening in the wellbore or not. So let's click on this one and select the static side and click on save, and then click on calculate bottom hole pressure. So what I did, I only adjusted the well data I click on the well data. In the well data, I selected flow path to be tubing and leave compute through quiet side and click on save. And this is the flowing bottom hole pressure. Right? Why I selected the compute through flowing side? Let's quickly take a look at the liquid loading. And the liquid loading, say the rate is definitely producing above the turning rate. So there is no liquid loading is happening in this one. Right? Can safely say that. Not only that, but also looking at the data itself, it's very smooth data, and very characteristic of liquid loaded well is the sporadic data. In this case, I don't see any sporadic data. This is very nice, clean data set that we are analyzing right now. So there is no actually the liquid loading is happening. The other piece of information I have is simply by looking at the casing and the tubing data. So I'm gonna include this casing and deselect the bottom hole pressure. So we select all of them and only focus on casing and the tubing. A very good characteristic of this not liquid loaded valves is that the casing and the tubing follow each other very nicely. So if there's a liquid loading happening, the liquid loading is happening in the tubing, and they're going to be over time, the difference between the casing and tubing going to be spread apart. But in this case, I can see the data. It's a quality check of the data I have to do in order to confirm there's no liquid loading is happening. So with the bottom hole pressure and PBT, let's go to analytical RTA. And in the analytical RTA, I want to expand this one and I want to see how my data look like here. So I'm going to adjust the data over here. Not interested in time to end of linear flow. I'm interested in observing the early time data. The early time data, this is, I believe, the line going through the data. I don't exactly know what happened, why the data drifted this way instead of moving upward. So I leave it for now here. But what's really important to me is there's an intercept here and the linear flow parameter is close to 63,000. That's the two important parameter for now. And you may argue, okay, what people refer to this intercept, a lot of people call it a skein, but a skein is a very general term. A finite conductivity reservoir, a fracture could be a skein. Wrong initial pressure could be a skein. Multi-phase flow could be a skein. A lot of things could be a skein, right? So what I'm gonna do right now, I'm gonna adjust the initial reservoir pressure. So I say one of the reasons why there's an intercept here because there's an initial reservoir pressure which could be uncertain to us, right? So if I adjust this initial reservoir pressure instead of 38, I'm gonna set it 30. Redo the calculation. Now my data drifted downward and I can adjust the initial reservoir pressure so there's no intercept. So simply the wrong initial pressure, wrong initial reservoir pressure can manifest itself in a positive intercept. So if we believe our initial reservoir pressure is 38.29, then this intercept is real. And now I want to see if finite conductivity causing this intercept, or it could be a fracture phase scheme, because they are totally different thing, or it is multi-phase flow. It could be many different reasons, or it could be turbulency that caused this intercept as well. It's also a scheme, right? So I'm gonna deal with this intercept, what is the source cause of this intercept? And for that, we need to do derivative analysis. So the derivative analysis is again, we do it here. So we say anytime that we're going to do flow regime identification, with the flow regime identification to identify if it is a bilinear or if it is a skein or if it is linear, we do derivative analysis. And the derivative analysis, we always do it in the log plot. So first of all, you can see, you might argue if this valve is boundary dominated or no. I'm going to leave here. For the boundary dominated, we plot our data on the log plot and we add unit slope. So at this point, you see it's not anymore PTA course, it's an RTA course, right? But I don't mind because they are integrated part of each other. So if you have the leverage, if you have the luxury having PTA data, you first need to accomplish this step before moving to the PTA work. So they are very complementary. That's why that's the main intent of doing PTA in the unconventional work, is to get some idea about the fracture properties, right? But let's see on the production side, because we have very clean production side, can we identify something? So with the flow regime identification, the first thing I'm gonna do is to see some of these data are lined up as a unit slope, and you can clearly see these, right? These are the lineup on the unit slope. So I wonder if it is simply artifact of the material balance time function that I'm using, or what could be the source cause of that. And for that, what I'm going to do, I'm going to highlight this data. Let's go ahead and use this feature, lasso highlight, and lasso highlight all the data that they present themselves on the unit slope line, right? So now this data are highlighted, and no surprise, they show themselves in a very low flow rate. The sudden drop in the rate profile which manifest themselves. Look at this data. These are the data that show themselves in the unit slope in the type curve plot. So very sudden rate change, especially drop in the rate profile, which manifests itself in the unit slope line in the type curve plot. So we should be wary of this if there are a lot of these happening over here, and they're going to present them a very nice unit slope, and you may argue, well, my reservoir is in the boundary dominance below by now. Well, as a matter of fact, it is not. It could be easily fooling you simply because this time function, the way it works, is bias the low rate data in the unit slope line. Right? Okay, so let's go here and also include the derivative. This is the derivative. So I can get anything meaningful out of these. Yes, I can identify some trend over here, but this is the cloud of the data. So I would say it's not very conclusive to work with the derivative, even though the production data are very clean. Right? So I can still include some of these half a slope. Maybe some part of the data show half a slope. Other part of the data at also quarter slope. Is really personal judgment at this point that you believe this data is half a slope, quarter slope, etc. So this is from the drawdown piece. Let's go to one more time, analyze this one, and I'm gonna adjust the slope a little bit over here. So this is gonna be my best interpretation. I know I'm using material balance time function. If I use a linear superposition, the data adjusts a little bit, but the early time doesn't change that much, right? So I'm comfortable with using material balance, despite the fact that I know material balance is not the best time function, is not the most accurate, but it's 70% of the solution there. So that's the best I can do. By the way, or in the future, we're also adding another feature here, another time function, which is a corrected pseudo time. That's a different story, 100 day. But let's proceed with the PTA part of this and the production data. So in the production data, we saw there's a period of drawdown followed by a period of buildup. And for the buildup, now we need the bottom hole pressure. How to calculate bottom hole pressure? We need to convert from surface to bottom hole. We convince ourselves that there's not much multi-phase flow going on, so I can safely use the casing pressure to convert to bottom hole pressure, and that's what I'm gonna do. In order to do that, we're gonna go bottom hole pressure, because by default the software doesn't calculate bottom hole pressure when the wellbore is in shutting. So what we should do, we should modify the calculation over here. So if you go click on the edit button one more time and go to this gear icon, and there's an option at the top, say by default, say do not compute when the well is in shutting. We somehow convince ourselves and feel confident that the wellbore is filled with gas during the shutting period, and therefore I'm gonna use compute shutting assuming gas filled wellbore. That's what I'm gonna do. I'm gonna save it. I'm gonna save it here, and I'm gonna rerun bottom hole pressure calculation. Okay, so let's see how the bottom hole pressure, all of them are, all the bottom hole pressure calculation, by the way, are predicting the same. Why? Simply because it's a gas reservoir, right? There's very small change in during the drawdown. I believe it's a very slight change. But during the build-up, there should be no difference between any of those calculations, simply because there is not much multi-phase flow going on. So this is a nice build-up pressure. Let's go ahead and do this analysis here. But before that, we need to go to production data and edit production data, scroll down all the way where we see blank cells. So our truncation feature be able to identify that shut-in period more over here. Okay, this is the first shut-in, extended shut-in. There are multiple shut-ins, but I'm interested in analyzing this extended shut-in. Drag it all the way to the end, populate the cells with 0, click on save. Oh, my radar shut-in. I can go to PTA. So the first thing first, you should switch to phase gas. And when you switch to phase gas, the truncation feature already identified that shut-in pressure. So I don't want to mess with that. And look at the derivative here. It's a very nice derivative data, right? In terms of that's the beauty of the build-up data, that at the end of the day, we have very clean derivative data. So this is a multiply horizontal wall. The time function that they're going to select is going to be either linear or bilinear. So we're going to select maybe a start with the linear. And now let's add some quarter slope and half slope. Adjust the zoom a bit, just furthermore. I don't see any well-bore storage. The best the resolution of the data here, by the way, is a daily resolution. So if you may wonder what's the best resolution for the PTA, 20-second data to start with is the best resolution, very good resolution. And after 2 days, 3 days, we can bump it up to 1 minute resolution. That's in terms of the resolution of data, if you're interested. So these are the two lines. So see, the early time is clearly showing a bilinear flow, right? It's showing a bilinear flow. And then it transitioned into a linear flow. So the build-up data convinced me that the fracture is finite conductivity is not a scheme, is a finite conductivity fracture. This is the type curve analysis, flow regime identification, and this one with the analysis itself, it's a Horner plot, right? The Horner plot shows very nice straight line, and you now have a very good idea. If I adjust the slope of the line, if I move it, I don't adjust the slope, the line stay there. But if I adjust the slope, the derivative also adjusts himself. So I'm gonna use this spray fit con option and adjust this data, and now it's everything turned back to where it was. I did all of this exercise only to compare two parameters: linear flow parameter during buildup, linear flow parameter during RTA, during production. 69,000. 65,000. It is impressive, honestly, when I saw this data, and it's the first time I saw this data. By first time, I mean I didn't have the opportunity to take a look at the production data followed by build up and do those comparison. Am I lucky to see this data? I believe I saw. I'm a little bit lucky. The data that the linear flow parameter are so close to each other is also another part, which is very interesting. Be in this case, could be for any other case. We didn't manipulate the production data. We adjusted the initial reservoir pressure a bit, but that doesn't change the story. I have to also emphasize that the pseudo time that we use during production is different from the pseudo time from the PTA, but the fact that they are in the ballpark is a very good thing. The fact that the derivative on the PTA side, show bilinear and then linear, is also a very interesting point. So this is the full RTA PTA analysis on this well. Spend some time, just manipulate the data a little bit, share your findings with us. If you are interested to have a conversation on it, definitely reach out. We definitely love to hear your feedback. So this is the first time that we are rolling out this course. We're gonna add a lot. We can see a lot of opportunity of adding a lot of things here. So please, it would do us a great favor if you do so, and provide your feedback in terms of other functionality that you would love to see. We already are aware of some of the missing part here, so we didn't get a chance to get those in the software for this course, but it is in our wish list. It is all on our backlog. So we're constantly working with our developer in order to include it. But what you can mature this software is your feedback, your constructive feedback. So there's another example. I'm going to quickly show that to you. Is about the it's a very similar story here, but with the multi-brag oil well, right? So in terms of the production data, I'm going to quickly show you how the pressure build up. If I can get that. Yes, the pressure should be there. Yeah. I prepared a couple of slides and I want to talk to them as well. So this is how the pressure build up. This is the pressure build up. We did this analysis on the flow and build up, and yeah, a very similar story, very similar workflow, and we also identified there bilinear followed by linear. Know that the gas is more definitely exciting and interesting example here, and let's see what we have here. Injection follow-up, we covered that. Complex reservoir model, depending on the it could be very much the derivative code should be different. The slope is stabilized at different slope, right? It could be very well associated to complex reservoir, to composite reservoir. So you can do the early time analysis, late time analysis, and as you show from the also specialized plot, that there are two distinct slope here, and it could be vice versa. It could be starting at a high, a shallower slope, and then a bigger slope there. It's really important for integrated study here. If you have RTA, PTA, you can marry them and get insightful information from one another. That would be definitely the road that you should, the workflow that you should go through. Data validation is the critical, the most important part of it is like sharpening your axe before it start to hitting the tree, right? That's the data validation. The wellbore dynamic, as it could be much more complicated. I couldn't cover all of these, but I was really interested to highlight the most important key, the key parameter for the wellbore dynamic. At the end of the day, what you are analyzing is the combination of wellbore and reservoir. So you should be able to learn from your experience. There's not much textbook describe the exact definition of wellbore, so it's mostly coming from your experience. And all the thing that matters is integrating the related information. If you have any question, I would be definitely happy to hear your thought. But at the end of the day, I would really like to appreciate one of the developer. A lot of people helped me, by the way, to get to this code ready for today. But Hassan was definitely the key contact. Was working day and night on getting this product out, and I'm glad had the opportunity to present it to you today, and appreciate your time staying with me for 3 hours. And but this means that please reach out if you have some data. I definitely would love to see those data. It definitely benefit me more than I guess benefit you guys, because the more I see this data, definitely I can fine tune the content of the course. Your feedback highly appreciated, and we cover the example, I guess. Thank you so much, Dennis.
Thank you very much, Hamid.
My pleasure.